Sometimes all it takes is a glance at the night sky, or a pause in a completely silent room, to feel as though the world around us is made mostly of empty spaces. Between the stars, between familiar objects, there seem to be vast regions where nothing happens at all. Space appears like a dark backdrop, a quiet stage on which the universe places planets, galaxies, and distant points of light. But science often begins by gently dismantling what seems obvious. Over the past century, physics has discovered that even the emptiest regions we can imagine are not entirely still. Energy can exist there even when no particles are present, and extremely subtle activities continue in places where the naked eye sees only emptiness. It turns out that the idea of nothing at all is far more complicated than intuition suggests. In everyday life, we rarely need to think deeply about this. An empty glass simply means a glass with no water in it. An empty room is one without people. A quiet street late at night is a place where movement has faded away. In these familiar meanings, empty is simply the absence of something. Something that used to be there has disappeared, or something we expected has not appeared. Yet even in these simple examples, emptiness is never absolute. An empty glass is still full of air. An empty room still contains light, temperature, and pressure. Even silence carries tiny vibrations. In other words, what we call emptiness is often only empty relative to what we expected to find there. Language strengthens this intuition. Words like nothing, nowhere, or emptiness evoke the image of a perfect void, a place without matter, without activity, without any influence at all. In everyday conversation, we use these words quite freely, without needing them to be precise. Physics, however, is not so forgiving. When science asks about emptiness, it always comes with a very specific demand. Empty of what? Empty of matter? Empty of particles? Empty of energy? Or empty even of the invisible forces and structures of nature? Each possibility is a different claim, and each claim must be tested by measurement. For physics, then, the question is not how empty a region of space appears to be. If that region still has measurable properties, or produces observable effects, it is not truly empty in the scientific sense. In the classical picture of physics, this distinction once seemed fairly simple. Matter was made of particles. Energy was associated with motion, heat, or radiation, and space itself was merely a passive stage. Once the particles were removed, what remained seemed like a quiet background, an empty container in which events could occur, but which did not itself participate. This view matched everyday experience. Remove all the objects from a room, and the room appears empty. Pump the air out of a container, and we call it a vacuum. The less matter there is, the closer space seems to approach a state of nothing. Yet quite early on, some scientists realized that this emptiness was not so simple. Consider air. For much of human history, air was treated almost like nothingness, invisible, weightless to the senses, and seemingly without material substance. It was only in the 17th century, through the experiments of Evangelista Torricelli and Blaise Pascal, that scientists demonstrated that air has mass, exerts pressure, and occupies space. Once again, something that had once been regarded as nothing turned out to be something that could be measured and studied. And that story has repeated itself many times throughout the history of science. There is something quite interesting in the history of science. Whenever humans look a little more closely into what seems to be empty, something that appeared to contain nothing begins to reveal structure. Layers of extremely subtle activity gradually emerge, and what was once considered absence turns out to be a form of presence that is simply difficult to notice. This is not because scientists want to make simple ideas unnecessarily complicated. It is simply that nature does not follow our intuition. In physics, the question of emptiness is actually quite precise. It is not an abstract meditation on nothingness, but a physical statement. In a particular region of space, what exists and what does not. Saying that we cannot see anything there is not enough. Vision has limits. Measuring instruments can extend human perception far beyond the senses, and they often detect activity in places where the naked eye sees only complete stillness. For that reason, if a region of space can generate forces, store energy, transmit motion, or influence matter elsewhere, physics must treat it as something. It cannot simply be called nothing. This is why defining emptiness becomes the first step of science rather than the last. Before an experiment is designed, before data are interpreted, we must understand clearly what absence actually means. Otherwise, new discoveries might be misunderstood or even overlooked simply because they do not fit the initial assumption that a place is completely empty. A familiar example is the concept of temperature. Absolute zero is not simply an intuitive feeling of extreme cold. It is defined by a precise physical limit, the state in which thermal motion reaches its lowest possible level. In a similar way, emptiness in physics must also be described using concrete quantities. What is the lowest possible energy level of space? What minimal level of activity is still permitted by the laws of physics? These questions belong to measurement and theory, not to the casual use of words. Yet the human mind has a special comfort with empty space. Objects seem clearer when placed against a blank background. Motion becomes meaningful when surrounded by stillness. For that reason, we often unconsciously treat empty space as a neutral backdrop, a passive absence that can be ignored. Physics does not allow that simplification. As understanding deepens, space itself begins to reveal properties of its own. It can be curved. It can store energy. It can oscillate and respond to changes occurring within it. At human scales, all of this is far too subtle to notice directly, and it never appears in a dramatic way. But subtlety does not mean insignificance. So rather than abandoning intuition, science is forced to refine it. The familiar emptiness of everyday life is only a starting point. A space empty of particles is not the same as one empty of physical fields. A space empty of matter does not mean it is empty of energy, and a region that appears empty in one theory may turn out not to be empty at all in another. Once definitions are slowed down and clarified, the picture gradually changes. Emptiness is no longer a single state, but more like a spectrum of different conditions. Some places are emptier than others. Some kinds of emptiness can be created by humans, and there are forms of emptiness that the laws of nature themselves may not even allow to exist. At that point, evidence can begin to speak clearly. Measurements start to carry the meaning of what they truly record, and the quiet assumption that nothing means nothing slowly loosens. This shift does not happen through dramatic speculation, but through patient observation. In the end, emptiness is no longer the destination reached after everything has been removed. It becomes the starting point of a question, and once that question is taken seriously, the idea of nothing suddenly turns into one of the most fascinating problems physics has ever faced. Perhaps this is also why, throughout much of human history, the idea of absolute emptiness has made people uneasy. The thought that a place could exist where absolutely nothing exists seems to challenge intuition, reason, and belief all at once. In the view of ancient thinkers, nature seemed to exist in a state of fullness. Every motion had a direct cause. One object pushed another. One substance acted upon another. Imagining a region completely devoid of substance, without resistance, and without any cause capable of producing motion, sounded less like a scientific possibility and more like a paradox. What is notable is that this skepticism did not arise from superstition or ignorance. It emerged from a serious attempt to build a coherent picture of the world. Ancient natural philosophy was highly structured and valued consistency and order. Within that framework of thought, the idea of absolute emptiness seemed to create more problems than it solved. One of the thinkers who shaped this view most strongly was Aristotle. In the 4th century BCE, he argued firmly that a vacuum could not exist. His reasoning was not based on intuition alone. It was deeply connected to his broader understanding of motion, causation, and the nature of matter. According to Aristotle, all motion requires a medium. Objects always move through something. They cannot move through nothing. If a vacuum truly existed, he argued, motion would become meaningless. Without resistance to limit speed, objects would accelerate infinitely. For Aristotle, this was not merely implausible, it was logically unacceptable. In an ordered universe governed by reason, infinite speeds had no place. From this perspective emerged a principle, later summarized by the phrase, "Horror vacui nature abhors a vacuum." Although the term itself was coined after Aristotle's time, it reflects the spirit of his argument. If a region of space appears empty, something must inevitably fill it, even if humans have not yet recognized what that something is. The influence of Aristotle proved remarkably enduring. For nearly 2 millennia, his writings shaped how people thought about nature. Throughout the Middle Ages, these ideas were preserved and expanded, blending with theology and logic in both Europe and the Islamic world. Natural philosophy gradually became part of a broader system of worldview. In that context, the question of whether a vacuum could exist was no longer merely a scientific issue. It became a challenge to the entire understanding of the universe. If the cosmos was assumed to be complete, continuous, and purposeful, then absolute emptiness simply had no place within it. Asking whether nothing could exist was often regarded as asking the wrong question from the start. As a result, many debates of that era focused on proving that a vacuum could not exist rather than attempting to test it. Arguments relied more on logical consistency than on measurement. When observations seemed to contradict theory, the phenomena were often reinterpreted in ways that preserved the underlying philosophical framework. There was also a very practical obstacle. Even if someone suspected that empty space might exist, there was no reliable way to create it. Air, at the time, was almost invisible to scientific understanding. It was not yet recognized as a substance with mass and pressure. Sealing a container or removing air from it therefore seemed to produce no obvious difference. Without tools to manipulate pressure, emptiness remained an abstract idea. The combination of philosophical conviction and technical limitation kept the notion of empty space at a safe distance. Nature was assumed to be full. If a gap appeared somewhere, it was treated as an illusion or a misunderstanding. In the imagination of that time, the universe resembled a continuous fabric of matter and influence, a structure that allowed no holes to exist. And there was a gentle irony in this attitude. The so-called fear of the void was not an emotional fear. It was a logical concern. A vacuum threatened to collapse carefully constructed systems of explanation. Rejecting the vacuum therefore became a way of preserving the stability of theoretical order. And it must be admitted that this approach worked reasonably well for a long time. Aristotle's physics explained many everyday observations. Heavy objects fall downward, fire rises upward, and different materials behave differently when they move. Within the limits of ordinary experience, the world seemed not to require the concept of absolute emptiness. But as observation became more precise, cracks began to appear. Water pumps could not lift water beyond a certain height. Suction behaved in strange ways. Pressure began revealing effects that no one had previously predicted. These were no longer abstract philosophical questions. They were practical problems. And practical problems often force people to ask new questions. Yet raising those questions still required a certain degree of courage. To doubt the impossibility of the vacuum meant challenging centuries of accepted knowledge and beginning to treat nothing not as an error, but as a hypothesis that could be tested. For a long time, people hardly distinguished between air and space. Both were invisible, and neither seemed to offer resistance when objects moved through them. So if a container appeared empty, it was simply assumed that there was nothing significant inside. The idea that air itself might be a form of matter took a long time to be accepted. Before that realization emerged, the concept of emptiness remained vague and difficult to define. This shift in understanding did not arrive suddenly through a grand theory. It began with very practical problems. One of them concerned the task of pumping water to higher levels. In the early 17th century, engineers working with mines and wells noticed a curious limit. Suction pumply, no matter how carefully constructed, could only raise a column of water to a certain height. Beyond that point, the water stopped rising. and above it appeared a space that looked empty. This puzzled them. If the mechanism worked by pulling water upward, then a stronger pull should lift the water higher. But that never happened. The column always stopped at around 10 meters. For decades, this phenomenon was treated merely as an inconvenient mechanical limitation, rather than a clue about the nature of the world. Then someone chose to look at the problem differently. That person was Evangelista Torricelli, a student of Galileo. In the early 1640s, he proposed a bold idea. Perhaps the water was not being pulled upward at all. Perhaps it was being pushed upward by the weight of the air covering the Earth. To test this hypothesis, Torricelli replaced water with mercury, a liquid far denser than water. Mercury is about 13 times heavier, so if air pressure were truly responsible, the required column of liquid would be much shorter. He filled a glass tube completely with mercury and inverted it into a basin of mercury. When the apparatus was set up, the mercury inside the tube dropped, leaving above it a space that appeared completely empty. The remaining column stabilized at a height of about 76 centimeters. The result was striking. It not only supported the idea of atmospheric pressure, but also produced something entirely new, a region of space that seemed to contain nothing at all. No stream of air rushed in. No visible substance filled the gap. Torricelli called it a vacuum. This was no longer emptiness debated in philosophical arguments. It was an empty space deliberately created inside a glass tube, under controlled conditions. For the first time, people could point to emptiness, measure around it, and discuss it as a physical phenomenon. Blaise Pascal soon extended the idea. If the column of mercury was being pressed down by the weight of the air above it, then at higher altitudes where less air lies overhead, the pressure should decrease. Pascal arranged for Torricelli's experiment to be repeated at different elevations, including on the summit of a mountain in France. The results matched the prediction. At greater heights, the mercury column was lower. This showed that air truly has weight, and that its pressure changes with altitude. These experiments quietly created an important separation. Air was no longer treated as invisible nothingness. It was a substance with mass, with pressure, capable of acting on other matter. And if air could be removed, then emptiness was no longer merely an abstract word. It became a condition that could be produced, even if imperfectly. At the same time, however, the experiments also revealed the limits of this new achievement. The vacuum above the mercury column was not nothing in the absolute sense. It contained no air, but it was not completely isolated from every influence. Light still passed through it. Heat still moved across it. And whatever existed in that space clearly did not behave like a perfect absence. Later vacuum chambers encountered similar limitations. Thus, the transformation in how people understood nothingness did not occur in a single moment. It emerged gradually, as more and more phenomena refused to fit the old assumption that the universe must always be completely full. These irregularities accumulated until emptiness was no longer a forbidden idea, but an experimental objective, something that could be created, tested, and observed. In retrospect, rejecting the vacuum had not been a mistake in the ordinary sense. It had been a reasonable conclusion given the limitations of available tools and the desire to preserve coherence in the scientific picture of the world. But as observations became sharper and experiments more refined, the universe seemed quietly to signal that it was time to ask questions in new ways. And once emptiness could be tested rather than merely debated, the idea of nothing began to transform from an impossibility into one of the most fertile questions in science. The earliest vacuum pumps improved only slowly, and they never achieved complete emptiness. Even after most of the air was removed, traces always remained that were difficult to eliminate. Tiny amounts of residual gases in the environment, water vapor clinging stubbornly to surfaces, and microscopic particles gradually released from materials over time. Even the best vacuums of the 17th century were only partial forms of emptiness. And this distinction turned out to be important. A space without air is not the same as a space without anything at all. The experiments of Torricelli and Pascal did not truly prove that absolute emptiness existed. What they demonstrated was something more modest, yet far more useful. Air is not the same thing as space, and removing air does not eliminate every physical effect. Once people recognized that air could exert pressure, they were forced to treat it as a real substance. And if a substance can be removed, then emptiness can at least be created to some degree. This realization also brought about a subtle psychological shift. Once air became something that could be measured, it lost its status as an invisible void. It became another component of the physical world, subject to the same laws and limitations as everything else. In doing so, it inadvertently freed the concept of space from its former role. If air was not space itself, then perhaps space could exist independently of whatever filled it. Even so, early vacuums were extremely fragile. They depended on the quality of the glass, on the skill of sealing the apparatus, and on pumps operated by hand. The emptiness they produced never lasted indefinitely. Over time, air would leak back in. Surfaces would release gases trapped within the materials. The vacuum gradually degraded. This imperfection kept scientists' expectations grounded. No one seriously claimed to have created absolute nothing. On the contrary, experiments suggested something even more intriguing. There always seemed to be something left behind. When one substance was removed, another influence remained. Air disappeared, and pressure disappeared with it, but light still passed through, and gravity was still present. Gradually, emptiness revealed itself as a layered concept, not a final state, but a process of stripping away successive layers. There was a quiet irony in this stage of discovery. Scientists began with the goal of creating nothing, only to realize that before they could approach that nothingness, they had to remove countless things they had not even realized were there. Yet the most important change was not how empty the space became, but how scientists approached the problem. Emptiness was no longer dismissed simply by philosophical argument. It had become an object that could be explored through experiment. And with that shift, a quiet turning point occurred. Questions that once belonged to philosophy began to become questions of physics. Separating air from space opened an entirely new conceptual gap. A region could be empty of one thing while still containing others. Emptiness became relative, conditional, and precisely definable. The small, empty region above Torricelli's Mercury column did not answer every question, but it allowed deeper ones to be asked. What remains when matter, energy, and perhaps even fields are removed? From that small void, a new picture of the universe slowly began to form. Space could now be imagined as something distinct from whatever existed within it. And from this separation emerged one of the most influential ideas in physics: absolute space. By the late 17th century, Isaac Newton articulated this idea clearly in Philosophiae Naturalis Principia Mathematica, published in 1687. According to Newton, space is real, fixed, and independent. It exists whether or not any objects occupy it. It does not depend on motion, nor does it depend on an observer. It simply exists. Within Newton's framework, space is not a substance like air or water. It has no texture, creates no resistance, and does not act on its own. Instead, it serves as a universal frame of reference, a perfectly still background against which motion can be measured. Objects move through space. Forces act within it, but space itself remains unaffected. This idea solved several problems at once. Motion could now be defined clearly. An object does not merely move relative to other objects, but also relative to space itself. Acceleration therefore retains meaning even if an object exists in isolation. Newton illustrated this with his famous thought experiment of the rotating bucket. When the bucket spins, the surface of the water curves upward along the edges. That curvature reveals that the rotation is real, not merely motion relative to the bucket, but motion relative to absolute space. In this picture, emptiness functions like a passive stage. If all matter were removed from a region of space, nothing fundamental would change. Forces would still obey their laws, and any object entering that region would behave exactly as the laws of physics predict. In the picture of classical mechanics, space plays almost no role other than simply being there. It does not react, It does not interfere, and it does not participate in the events that occur within it. Space merely provides position, distance, and direction. Time provides the duration of processes. Together, these two elements form a stable framework, an invisible scaffolding on which particles move, collide, and interact. This was not regarded as a shortcoming. On the contrary, it was an advantage. By keeping space silent, physics could focus on the main characters of the story, matter and force. The equations became cleaner, calculations became manageable, and predictions reached astonishing levels of accuracy. Planetary orbits could be calculated years in advance. Cannonballs followed familiar curved paths. Tides rose and fell under the gravitational influence of the moon. The usefulness of this model is difficult to overstate. For centuries, it worked remarkably well. Even today, much of human engineering still rests upon that foundation. Bridges are built, satellites are launched into orbit, and machines operate with precision, all based on the assumption that space is a stable, empty background. There is a quiet elegance in this view. Space does not protest, does not demand attention, and does not complicate the equations. It provides a silent consistency in which the laws of physics can shine. In that sense, emptiness was not merely accepted, it was welcomed. Yet this silence came with hidden assumptions. When classical mechanics declared space to be inert, it simultaneously ruled out many other possibilities. Space could not store energy. It could not transmit influences on its own. It could not change shape or properties. If something happened, it had to be because matter acted on matter, through forces operating across space, but not belonging to space itself. It is precisely here that the mechanical view begins to reveal its limits. It treats space as a container, rather than as a participant. If everything were removed from a region, the assumption was that nothing physically meaningful would remain. Even gravity in Newton's system fit comfortably into this picture. Objects attract one another across empty space, yet space itself remains unchanged. It merely allows the force to pass through without contributing to the process. Newton himself found this troubling. He famously refused to speculate about the mechanism by which gravity could act at a distance. But the equations worked, and for the physics of that time, that was enough. There is a certain pragmatism in this approach. Physics does not demand philosophical completeness. It demands accurate prediction, and the mechanical view of empty space delivered that success again and again. At human scales, everything seemed to confirm the assumption. A spacecraft drifting between planets encounters almost no resistance. A stone thrown into the air traces a smooth arc. Inside a laboratory vacuum chamber, experiments proceed without interference from air. In all these situations, space appears to do nothing at all. This very silence reinforced the belief that emptiness was truly empty. If no effects appeared, it was easy to conclude that nothing existed there. But science often advances by paying attention to the quietest details. Over time, questions began to emerge. If space is completely inert, how does light travel through it? Light is not a material object. It has no mass. Yet it always moves at a fixed speed, the same for every observer, regardless of their motion. This behavior does not entirely fit a picture in which space is merely a passive background. Small inconsistencies also began to appear. If motion is measured relative to absolute space, why does that space never reveal itself directly? Why can it never be detected, pushed, or disturbed? Newton himself acknowledged this unease, even though he continued to rely on the concept. And because the mechanical model worked so well, the deeper questions were simply postponed. In science, postponed questions are not forgotten ones. They are merely waiting for the right moment. The silence of empty space, so useful and so convincing, gradually became something that needed to be listened to more carefully. As measurements grew more precise and new phenomena were discovered, especially those involving light and electromagnetism, the assumption of a completely inert background began to face pressure. Yet at this stage, emptiness still behaved obediently. It stood still, allowed motion to occur, and demanded nothing in return. That very obedience made it one of the most effective ideas physics had ever used. Then light began to reveal the hidden assumptions behind it. For centuries, light had been both familiar and mysterious. It reflects, refracts, scatters, and travels across enormous distances, often passing through regions that appear completely empty. As understanding of light deepened, it began to place quiet pressure on the idea that empty space truly contains nothing. In classical mechanics, an object in motion does not require a medium to carry it. A thrown stone continues along its trajectory. But waves are different. Sound waves require air. Water waves require water. Oscillations seem always to be tied to the material that supports them. By the 18th and 19th centuries, light was increasingly understood as a form of wave. And immediately, a question arose. If light is a wave, what exactly is waving? It travels across the space between the sun and the earth, through regions where air cannot exist. It crosses the vast gaps between stars and galaxies. If space truly contains nothing at all, then light appears to have no medium to carry its motion. As light came to be understood increasingly as a form of wave, physics faced an uncomfortable choice. Waves, according to familiar intuition, always require a medium. Sound waves need air. Water waves need water. So rather than abandoning the wave description of light, physicists sought another solution. They imagined a new, subtle and invisible medium called the luminiferous ether. In this picture, the ether permeated the entire universe. It filled every region of space, even those completely devoid of matter. Yet it was unlike air. It had no weight. It offered no resistance to the motion of planets or other objects. Humans could neither see it nor feel it, and yet it was believed to provide exactly what light waves required: a medium through which they could oscillate and propagate. The idea had a peculiar appeal. It allowed light to remain a wave while preserving the familiar assumption that space itself was inert and passive. Space could be empty of matter, yet quietly filled with a subtle substance no one could perceive. Emptiness, in this sense, was preserved in name, even though in practice it had been filled. Many leading physicists accepted this picture. When James Clerk Maxwell developed the equations of electromagnetism in the mid-19th century, he described light as oscillations of electric and magnetic fields. These oscillations appeared to require a medium in which they existed, and the ether seemed to fit that role perfectly. It became the invisible stage on which all electromagnetic phenomena unfolded. But the very features that made the ether attractive soon turned it into a problem. To transmit light at such enormous speeds, this medium would have to be extraordinarily rigid. At the same time, it would need to remain completely undetectable as objects moved through it. The Earth orbits the Sun at roughly 30 kilometers per second. If the ether truly filled space, our planet should constantly be moving through it. In that case, the speed of light measured on Earth ought to vary depending on the direction of motion, much like a cyclist experiences different wind speeds depending on whether they ride with or against the wind. To search for this effect, scientists designed extremely delicate experiments. The most famous was carried out by Albert Michelson and Edward Morley in the late 19th century. They compared the speed of light along two perpendicular directions, hoping to detect a tiny difference caused by the Earth's motion through the ether. The result was puzzling in its simplicity. No difference was detected. Light appeared to travel at the same speed in every direction. Repeated experiments produced the same outcome. If the ether existed, it was behaving in a way that was extremely difficult to explain. A tension began to emerge. On one hand, the wave nature of light seemed to demand a medium. On the other hand, every attempt to detect that medium failed. The more carefully scientists studied light in empty space, the clearer the problem became. Light does not slow down in the space between planets. It does not scatter or weaken in a way that would suggest interaction with a material substance. It can travel across enormous cosmic distances with remarkable stability. Whatever exists in space, it does not behave like any familiar physical medium. This also created a conceptual discomfort. If the ether truly filled the entire universe, then space was not empty in any real sense. Emptiness would be only a manner of speaking, The universe would still be full, merely filled with something invisible and unresponsive. Here, a subtle shift was taking place. The idea of emptiness was being preserved not because evidence demanded it, but because abandoning it seemed premature. The ether quietly served to protect the familiar picture of space as a passive container of physical events. But light continued to behave in ways that placed increasing strain on that picture. Its speed appeared to be a fundamental constant rather than the result of motion through a medium. Observers moving at different velocities still measured the same value. This behavior resembled neither sound, nor water waves, nor any form of oscillation in ordinary matter. As measurements grew more precise, the ether became increasingly awkward. Various adjustments were proposed. Perhaps the ether was partially dragged along by the Earth. Perhaps objects moving through it would contract in length. Yet each modification made the theory more complicated without bringing real clarity. There is a gentle lesson here. When a concept exists mainly to protect an assumption, it becomes fragile. The ether existed to preserve the idea that empty space must be inert. But, as evidence accumulated, that protection began to look strained. Light seemed not merely to travel through empty space. It appeared to reveal something about space itself. Its speed set limits. Its behavior hinted that space might possess a structure of its own. By the end of the 19th century, the situation had become clear yet unresolved. Light behaved like a wave, but no medium could be found to carry it. Empty space could support electromagnetic phenomena, yet it did not behave like any substance humans had ever encountered. By the end of the 19th century, the mechanical picture of space began to come under pressure, not because it collapsed immediately, but because it had become too silent in the face of what scientists were observing. Light had made the idea of emptiness more complicated, yet it offered no clear resolution. It did not immediately destroy the old model, it merely created cracks. And once those cracks appeared, the assumption that space was nothing more than an empty stage for physical events became increasingly difficult to maintain. By that time, the concept of the luminiferous ether stood in a fragile position. It was still accepted by many physicists and carefully described within theoretical frameworks, but it had become increasingly difficult to justify experimentally. Light behaved exactly like a wave, yet every attempt to detect the medium carrying that wave had failed. The question was no longer whether the ether was elegant in theory or intuitive in concept. The question had become far simpler: did it exist at all? One of the scientists determined to answer this question was Albert Michelson, a physicist renowned for his extraordinary precision in measurement, particularly in experiments involving light. Together with Edward Morley, he set out to test a prediction that followed almost inevitably from the ether hypothesis. The reasoning was straightforward. The Earth orbits the Sun at roughly 30 kilometers per second. If the ether truly filled all of space, our planet must be constantly moving through it. In that case, light traveling in the direction of Earth's motion should take a slightly different amount of time compared with light traveling perpendicular to that motion. The difference would be extremely small, but still within the limits of careful measurement. To test this idea, Michelson and Morley constructed an ingenious device called an interferometer. A beam of light was split into two parts. Each part traveled along a path perpendicular to the other, reflected back, and then recombined. If the travel times along the two paths differed, the reunited beams would produce an interference pattern that could be measured. The experiment was carried out with extraordinary care. The apparatus was isolated from vibration. Measurements were repeated at different times of day and at different times of year, when the direction of Earth's motion through space would change. If the ether existed, its signature should appear somewhere in the data, but it did not. The result was not merely small, it was essentially zero. No matter how the apparatus was rotated, no matter when the measurements were taken, the speed of light remained unchanged. There was no indication that the Earth was moving through any invisible background medium. This absence could not easily be blamed on the equipment or the method. The interferometer was sensitive enough to detect effects far smaller than those predicted by theory. Quite simply, the expected signal was not there. The physics community found this deeply unsettling. Science is accustomed to encountering surprising results, but it is rarely comfortable when nothing happens, while theory insists that something must. The Michelson-Morley experiment did more than fail to confirm the ether. It began to undermine the entire idea. At first, physicists attempted to rescue the hypothesis. Perhaps the ether was partially dragged along by the Earth as it moved. Perhaps objects moving through the ether contracted in the direction of motion, cancelling the expected effect. Such explanations, proposed by Hendrik Lorentz and George Fitzgerald, were mathematically subtle, but physically strained. They could account for the result, yet they did not explain why the result occurred. The situation became more serious as experiments were repeated. New variations of the Michelson-Morley experiment were performed with increasing precision. The outcome remained the same. Light behaved as if no medium existed, or more precisely, as if the laws governing light were the same everywhere, regardless of the observer's motion. This forced physics to reconsider the meaning of emptiness. The absence of the ether could no longer be dismissed as ignorance or experimental limitation. It had become a stable, repeatable, and verifiable result. There is an important point here. In science, failing to detect something once often means very little, but when it fails to appear repeatedly, under conditions where it should certainly appear if it existed, that absence becomes powerful evidence. The Michelson-Morley experiment turned emptiness into a measurable statement. It showed that motion through space does not seem to be defined relative to any hidden background. There is no absolute state of rest. There is no invisible medium marking the stillness of the universe. Instead, the laws of light appear to be the same for every observer, regardless of how they move. This was not a philosophical conclusion. It was an experimental result. Space does not behave like a medium. It leaves no trace of motion. It produces no drag, no pull, and no preferred direction. The old idea of an absolute space filled with an invisible substance began to lose its footing. What would replace it was not yet clear. This experiment told physicists what space was not, but it did not yet tell them what space truly was. The collapse of the ether did not occur as a dramatic explosion in the history of science. It happened quietly through a long sequence of null results that refused to disappear, and in that moment there was a calm honesty. Physics did not declare victory, nor did it rush to proclaim a new truth immediately. As the ether hypothesis gradually collapsed, physics did not respond with a loud revolution. Instead, it quietly accepted a simple fact. An assumption that had survived for too long no longer matched the data. Emptiness, once regarded as a gap in human understanding, began to demand a more serious place within physics. The disappearance of the ether also highlighted a deeper question. If light did not require a medium to propagate, perhaps the familiar intuition that all waves must have a medium was wrong. Or perhaps space itself possessed properties that had previously gone unnoticed. Either way, the image of space as a silent, inert background for physical events began to weaken. The Michelson-Morley experiment did not solve the problem of emptiness. It changed how the problem was asked. From that moment on, emptiness was no longer something that needed to be filled with convenient hypothetical substances. It became something that had to be understood in its own right. When the ether disappeared, physics did not return to a simpler picture. On the contrary, the door opened to a more daring perspective, one in which space and motion could not easily be separated, and in which the structure of space itself might play an essential role. The silence of the experiment spoke clearly. Whatever space might be, it was not an invisible ocean carrying light along. And whatever emptiness meant, it could no longer be dismissed as the result of insufficient investigation. It had become a measurable reality. At the beginning of the 20th century, physics found itself in an uneasy pause. The ether was gone, yet no clear concept had replaced it. Light continued to move through space at a constant speed. Absolute motion seemed no longer to exist, and the old picture of space as a quiet container began to feel unsatisfactory. It was in this context that Albert Einstein appeared. He did not propose a new substance to fill space. Instead, he questioned the very nature of space and time themselves. In 1905, Einstein published a paper that would later be known as the theory of special relativity. The theory did not begin by describing what space is made of. Instead, it began with two principles that seemed deceptively simple. First, the laws of physics must be the same for all observers moving at constant velocity. Second, the speed of light in a vacuum is always the same for all such observers, regardless of how they are moving. These principles were not proposed for dramatic effect. They were a serious attempt to accept the results of experiment. The Michelson-Morley experiment had shown that light does not behave as though it moves through a medium. Einstein simply trusted that result and followed its logical consequences. The outcome was a fundamental shift. Space and time, which had once been regarded as separate and absolute, could no longer remain independent. Distances depend on motion. Time also depends on motion. Two observers moving relative to one another may disagree about how long an event lasts or how far apart two events occur, and both can be correct. This does not happen because clocks or rulers malfunction. It happens because space and time themselves are intertwined. Two events that are simultaneous for one observer may not be simultaneous for another. Lengths can contract. Clocks can run slower or faster depending on motion. These effects are not illusions. They are genuine properties of the world. To describe this new picture consistently, physicists began speaking of space-time. Space-time is not simply space plus time. It is a unified structure in which distances and durations are bound together. An event is no longer defined only by where it occurs, but also by when it occurs. This union completely changes the meaning of emptiness. An empty region of space is no longer merely a place without matter. It is a region with a specific space-time structure. Even when nothing exists within it, space-time itself still exists. It still possesses measurable properties, and it still imposes limits on what can happen. One striking consequence of special relativity is that the speed of light becomes the ultimate limit of motion, not because light encounters resistance, but because the structure of space-time itself does not allow anything to exceed that speed. This limit exists even in perfect vacuum, even in the absence of matter. That alone is enough to show that emptiness is not nothing. A region that can limit motion, define simultaneity, and bind space together with time cannot be considered inert in the classical sense. Another profound change also emerged. Once space and time became linked, measurements began to depend on the observer. Emptiness, once considered absolute, now became relative. Two observers moving differently through the same region of spacetime may not agree about its size or its duration. The distance between 2 points may appear shorter to one observer and longer to another. The time between two events may stretch or contract depending on motion. This does not mean reality becomes subjective. The underlying structure of spacetime remains consistent. It is simply that each observer slices that structure into space and time in different ways. Emptiness still has its geometry, but that geometry is not experienced in the same way by everyone. At first glance, the idea that time and space depend on the motion of the observer can feel unsettling. Yet these effects are not abstract speculation. They have been measured directly. Extremely precise atomic clocks, when carried aboard airplanes or satellites, actually run at different rates compared with clocks on the ground. Particles moving close to the speed of light in accelerators also exhibit clear signs of length contraction and time dilation. These phenomena do not exist merely on paper. They are real consequences of the structure of spacetime. This new perspective also resolved a lingering discomfort that had existed since Newton's time. Absolute space, which could never be detected directly, was no longer necessary. Motion no longer had to be measured relative to an invisible background. Instead, it could be defined purely in relation to observers, all of whom obey the same physical laws. Space therefore did not disappear. On the contrary, it became richer. It was no longer a silent box containing events, but part of the dynamic framework in which events occur. Even when no matter exists, space-time is still there. It still determines the paths objects can follow. It still dictates how clocks run. It still governs the behavior of light. There is a quiet irony here. When physics removed the ether, it did not return to nothing. Instead, it replaced the old invisible medium with a deeper and more abstract structure. Space-time is not a substance like water or air, yet it is not nothing either. It can be measured, modeled, and tested. It has geometry, limits, and physical consequences. The question of emptiness therefore becomes more subtle. Asking whether space is empty now requires asking, empty of what? It may be empty of matter, but it is not necessarily empty of energy, and it is certainly not empty of structure. Special relativity shows that even a perfect vacuum contains information about motion and causality. It determines which events can influence which others. It governs how signals propagate. These relationships exist even when no particle appears within that region of space. In this sense, emptiness becomes a contextual concept. A region may contain no atoms and yet still be filled with space-time relations. It may contain no particles and yet still impose the universe's speed limit and the ordering of time. However, this transformation was only the beginning. Special relativity reshaped our understanding of motion and time, but gravity still remained outside the story. In Newton's picture, gravity was still a force pulling objects across empty space, and that idea was increasingly difficult to reconcile with the new concept of spacetime. If spacetime itself determines motion, then gravity's role within that structure must be reconsidered. Einstein did not ignore this question. Over the course of 10 years, from 1905 to 1915, he gradually rebuilt the entire foundation of gravitational theory. The result was general relativity, a completely new description of gravity. In this theory, gravity is no longer a force transmitted through space. Instead, it is a property of spacetime itself. According to general relativity, matter and energy change the geometry of spacetime. Massive objects do not pull other objects toward them in the usual sense. Rather, they distort the structure of spacetime around them. Other objects simply move along the natural paths within that curved geometry. What we experience as gravitational force is actually motion along the geometry of curved spacetime. A familiar analogy is to imagine a stretched surface. When a heavy object is placed on it, the surface bends downward. Smaller objects roll toward the heavy one not because they are directly pulled, but because the surface beneath them slopes downward. Although the analogy has its limitations, it helps illustrate the central idea. Gravity is not something added to space. It is part of the very structure of spacetime itself. There was a time when classical physics viewed empty space as a quiet, featureless background. In Newton's picture, the space between celestial bodies was perfectly uniform, motionless, and devoid of any intrinsic properties. It was simply the place where objects existed. But general relativity completely transformed this understanding. Empty space is no longer necessarily flat. Even in the absence of matter, the geometry of space itself can remain curved and continue to exist as a structure that carries the imprint of influences from afar or from the past. This leads to a rather surprising conclusion. A region containing no matter at all can still affect motion. The curvature of spacetime can bend the path of light and alter the trajectories of objects passing through it, even though the region itself contains no particles. This phenomenon is not speculation. It has been observed. When light passes near massive objects, its path bends, an effect known as gravitational lensing. The first evidence appeared during the solar eclipse of 1919, when stars near the edge of the sun appeared slightly displaced from their expected positions. Their light had traveled through a region of space containing no matter, yet its path curved because the spacetime around the sun had been distorted by the star's mass. General relativity even allows more extreme situations. Einstein's field equations admit solutions in which the curvature of spacetime exists entirely without matter. These are known as vacuum solutions situations, where geometry itself persists and propagates without a material source present at every point. Gravitational waves provide a clear example. When enormous masses such as two black holes or two neutron stars spiral together and merge, they generate ripples that travel through the very structure of spacetime. These ripples move outward at the speed of light, passing through vast regions that contain no particles, while stretching and compressing space-time as they pass. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO directly detected this phenomenon, confirming a prediction that had existed for nearly a century. The instrument did not detect matter, nor did it detect radiation. What it measured was a change in the geometry of space-time itself. Space that seemed perfectly quiet was, in fact, oscillating. Within this theoretical framework, empty does not mean flat. It simply means the absence of matter and non-gravitational energy. Geometry remains, structure remains, and the laws of physics continue to operate. Gravity is therefore no longer viewed as a force acting within space. It is a property of space itself. Objects in freefall simply follow the straightest possible paths within curved space-time paths known as geodesics. There is a quiet elegance in this idea. Gravity no longer resembles an invisible hand pulling things together. It is more like the shape of a landscape. Space tells matter how to move, and matter tells space how to curve. And once that curvature forms, it does not disappear immediately when the matter leaves. Space carries a memory of what once existed. A region of empty space near a star is not the same as empty space far away from any mass. Both contain no particles, yet their geometries are different. The consequences of this difference appear everywhere. Light follows different paths. The motion of objects changes. Even time does not flow uniformly. Clocks placed in different locations within a gravitational field run at different rates, an effect known as gravitational time dilation. This phenomenon has been measured repeatedly and must even be taken into account in technologies such as GPS. A quiet paradox begins to emerge. The more matter is removed from the physical picture, the more important space itself becomes. What once appeared to be an empty stage turns out to be the structure that shapes motion, light, and time. Yet general relativity does not claim that space is filled with a hidden substance. It does not revive the concept of the ether in a new form. The curvature of space-time is not a material medium. It produces no drag and establishes no absolute state of rest. It simply possesses geometry, and that geometry determines how events unfold. In this sense, empty space is neither nothingness nor a material substance. It is a geometric state of the universe. And from this point onward, the meaning of empty space becomes entirely different from what it once was. Even when matter is absent, space is far from silent. It shapes trajectories, limits the paths that motion can take, and even carries ripples that propagate through its own structure. Yet when general relativity describes all of this in terms of geometry, another gap quietly appears. The theory explains the shape of space-time with remarkable elegance, but it says almost nothing about energy in regions completely devoid of matter. In that picture, space is geometry, not yet a reservoir of energy. And so, a question lingers. If an empty region can curve without matter, might the curvature itself carry some form of energy? The geometry of emptiness has been clearly established, but its energetic content has not been fully resolved. Once emptiness reveals that it possesses structure, it seems only to invite the next question. Can space store energy even when no particles are present? And if it can, what kind of energy would that be? While such questions were beginning to take shape, another revolution in physics had already been quietly unfolding. Long before space-time was described as curved, space had begun to acquire inhabitants of a peculiar kind, neither particles nor substances. They were known as physical fields. A field is not something you can hold. It does not flow or accumulate like matter. Instead, it assigns a value to every point in space and time, describing what would happen if something were placed there. A magnetic field tells you how a compass needle would turn. An electric field tells you how a charged particle would accelerate. Remarkably, fields exist even when no particles are present. This idea was developed most clearly in the 19th century by Michael Faraday. Faraday was not a mathematician in the traditional sense. He thought in images and experiments. He imagined space threaded with invisible lines of force that guided electrical and magnetic effects. To Faraday, these lines were not merely convenient drawings, they were real features of space. This represented a bold shift. Instead of forces acting instantaneously across empty space, influences were now carried locally through fields that filled the region between objects. Space was no longer simply the place where interactions occurred. It became the place where those interactions were encoded. James Clerk Maxwell later translated Faraday's intuition into mathematics. In the 1860s, Maxwell unified electricity and magnetism into a single framework, now known as classical electromagnetism. His equations showed that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. Together they sustain one another, forming waves that propagate through space. From this perspective, light no longer appeared as a mysterious substance or a mechanical vibration of some hidden medium. It emerged naturally as an oscillation of electromagnetic fields. Maxwell's equations predicted that these oscillations would travel at a speed determined by the electric and magnetic properties of space, a speed that matched the measured speed of light. Once again, particles were not required for the existence of the field. An electromagnetic field can occupy a region of space even when no charged particles are present there. The field is not created anew each time a particle passes through. Instead, it exists as a condition of space itself, shaped by sources elsewhere and by the boundary conditions of the system. This has an important consequence for emptiness. A region of space may be empty of matter and still contain fields. Those fields can store energy, transmit influence, and affect anything that later enters the region. Field energy is not merely abstract. An electric field between two charged plates genuinely stores energy that can later be released. A magnetic field carries energy and can exert pressure even in regions far from its source. Fields can even persist after the original sources have disappeared. Once again, the meaning of emptiness shifts. Removing particles does not remove structure. Space does not return to a neutral background. Instead, it retains a pattern of possibilities, a map describing how particles would behave if they were present. In classical physics, fields were treated as continuous quantities. Their values change smoothly from point to point. They can be strong or weak, curved or straight, but they do not come in discrete pieces. This makes them feel less like objects and more like conditions of space itself. And yet, their presence is undeniable. Without fields, forces would have no mechanism. Without electromagnetic fields, light would have no description. Without gravitational fields, motion would lose its guide. Fields also resolved a long-standing difficulty in physics. Interactions no longer needed to leap instantaneously across empty space. Instead, they could propagate at finite speeds through fields that occupy the region between objects. Space was therefore no longer empty between interacting bodies. It was filled with the very structures that made interaction possible. At the same time, fields did not behave like the abandoned ether. They did not define a preferred state of rest, nor did they resist motion uniformly. They remained entirely compatible with relativity. Their behavior could depend on the observer, but their existence did not privilege any particular frame of reference. Space, once thought to be empty between objects, had quietly become something far richer, a stage filled not with matter, but with the invisible structures that make the universe work. When the concept of fields emerged, it did not break the framework of relativity. Instead, it fit naturally within it. Fields exist in space-time, evolve through time, and all their influences are constrained by the universal limit set by the speed of light. In this way, they align perfectly with the geometric framework of the new universe. In classical physics, fields were imagined as smooth fabrics spread throughout space. Their values changed continuously from one point to another. At any location, a field could in principle be specified with arbitrary precision, and this fabric seemed capable of being divided without end. But that smoothness did not survive forever. As measurements became more refined and physics began probing smaller scales, cracks gradually appeared. Energy was not exchanged continuously, as once believed. It appeared in discrete packets. Light, which had been described as a pure wave, also began to display particle-like behavior. Fields that had been treated as perfectly continuous surfaces began to reveal a deeper structure, as though the fabric itself possessed a kind of grain. Yet before the transition to quantum physics took place, fields had already accomplished something crucial. They demonstrated that empty space is not physically empty. Even in the absence of matter, space still contains conditions, structures, and stored possibilities. Space was already busy long before any particle arrived. In this sense, fields became a natural bridge between two eras of physics. They preserved the calm continuity of classical physics while quietly preparing the ground for a far more dynamic world at the quantum level. They showed that structure could exist without substance, and that influence could exist without objects. Even when every particle is removed, something still remains. The geometry of space remains, the fields remain, and the laws remain. The blank background once called empty space now begins to resemble a textured surface, not crowded, not noisy, but unmistakably present. When fields can exist anywhere that physics permits, the concept of emptiness slowly takes on a different meaning. It is no longer the absence of everything, but the presence of things that cannot be seen. Recognizing this did not yet require quantum mechanics. It required only the acceptance that space carries more than position. It carries information, structure, and potential influence. And that acceptance opened the door to an idea even more difficult to accept. By this point, physics had learned that space could curve, fields could exist without particles, the geometry of space-time could guide motion even where no objects were present. Yet one more step remained, a step that made human intuition hesitate. Energy itself could exist without being attached to any object. In everyday experience, energy seems always to accompany matter. A moving car has energy because it has mass and motion. A hot stove has energy because its atoms vibrate. A stretched spring contains energy because it can snap back. Intuition suggests that energy must always belong to something doing something, but the definition used in physics is far broader. Energy is simply the capacity to produce change. Anything capable of altering motion, temperature, structure, or interaction possesses energy whether or not it is attached to a visible object. Fields reveal this immediately. An electric field can store energy even when no charged particles are moving within that region. A magnetic field can exert pressure, transmit momentum, and perform work. That energy does not vanish simply because no particles happen to pass through. It remains distributed in space. This is not metaphorical language. It can be measured. The energy stored in an electric field between two charged plates can be calculated and released. The energy density of a magnetic field can be detected through its physical effect. When fields shape space, space itself becomes a reservoir of energy. Gravity makes the picture more subtle. In general relativity, gravity is not a force, but the geometry of space-time, which makes gravitational energy difficult to assign to a single point. There is no unique location where gravitational energy simply sits. Instead, it is associated with the curvature of space-time as a whole. Difficult though it may be to localize, this energy is still real. Gravitational waves carry energy across the universe. As they pass through a region of space, they stretch and compress distances between points, performing work on anything that lies along their path. Instruments on Earth have detected this effect directly. The energy arrives not in the form of particles, nor as familiar radiation, but as changes in space-time itself. The crucial point is not the bookkeeping of energy, but its meaning. Empty space, when shaped by gravity, can carry energy even in the absence of matter. The energy is not stored in objects, it is stored in structure. This idea challenges human intuition because our intuitions were formed in a world where energy seems always tied to visible things. Fire burns fuel. Muscles work by consuming food. Water flows downhill. Energy appears whenever matter moves or transforms. Physics reveals a broader picture. Energy can spread out. It can be distributed thinly across space. It can exist as tension, curvature, or configuration within a system. It does not always require a container in the familiar sense. This becomes clear when considering gravitational binding energy. Two massive objects attract each other, forming a system whose total energy is lower than when the objects were infinitely far apart. The difference between those energies resides in the gravitational field between them. That energy does not belong entirely to either object. It belongs to the space between them. Electromagnetic fields behave in a similar way. An electromagnetic wave traveling through empty space carries both energy and momentum, even when no particles are present in that region. An electromagnetic wave traveling through empty space still carries energy with it. When it encounters matter, that energy can heat surfaces, push small objects, and even trigger chemical reactions. What is striking is that all of this can occur after the wave has crossed regions of space that contain no matter at all. Empty space, therefore, no longer resembles a passive backdrop. Even when all particles are removed, space can still store energy, carry it across vast distances, and redistribute it in ways allowed by the laws of physics. It still acts. This does not violate the law of conservation of energy. Energy is still conserved. It is simply not confined to objects. When physics analyzes a system, space itself becomes part of that system. And instead of asking where energy is located, physicists begin to ask how it is distributed. The answer often leads to regions that appear empty. For this reason, empty space is very difficult to make completely empty. Removing matter removes only one of the places where energy can reside. The geometry of space remains. Fields remain. Motion and influence remain. Each layer that is peeled away reveals another beneath it. There is a common intuition that when all matter disappears, nothing significant remains. Physics has repeatedly refused that simplification. Even when no particles are present, the conditions that determine how particles would behave still exist, and those conditions carry their own energetic consequences. This does not mean that empty space is like a battery waiting to be discharged. It only means that space participates in physical law. It sets limits. It transmits influence, and it responds to change. On cosmic scales, this becomes clear. The expansion of the universe involves energy associated with space itself. Gravitational waves can pass through enormous voids. Light can travel for billions of years through regions containing almost no matter, carrying its energy the entire way. At smaller scales, the principle is the same. Even before quantum mechanics appeared, classical physics had already been forced to admit that empty space is not energetically neutral. This unsettles a familiar way of thinking, the idea that energy must always belong to something. Physics answers that energy requires structure, and structure does not disappear simply because matter disappears. There is a calm directness to that fact. Nature does not adjust its rules to match human intuition. It simply operates according to consistent laws, and empty space follows those laws as well. By this point, empty space has accumulated far more properties than it was once believed to possess. It has geometry. It contains fields. It can carry energy. It becomes difficult to continue treating it as pure nothingness. Even when it appears perfectly still, it remains a component of the physical picture. Yet everything described so far still lies within the domain of classical physics. Fields are treated as smooth. Energy can change continuously. Space, though structured, behaves in a relatively stable way across all scales that had been examined. This quiet stability does not last forever. As the attention of physics shifted toward smaller scales and more precise measurements, a new kind of instability gradually emerged. Energy exchange became discrete, fields began to fluctuate, and space itself started to display activity that could not be smoothed away by classical descriptions. The idea that energy could exist without objects turned out to be only the threshold. Once energy is allowed to exist everywhere, even in empty space, a new question naturally appears. If energy can be present everywhere, what prevents it from appearing, disappearing, or fluctuating at the smallest scales? That question belongs to quantum mechanics, And once that question is asked, empty space is no longer a quiet background. By the early 20th century, physics had already learned to be cautious with the concept of stillness. Space could curve, fields could exist without particles, energy could exist without being attached to objects. Yet beneath all of this remained a comfortable assumption. If everything were removed, if motion stopped, and energy reached its lowest possible level, then a perfect state of rest must still exist, an absolute stillness. Quantum mechanics quietly removed that possibility. This was not merely a small adjustment to classical physics. It was an entirely new theoretical framework, built to describe the world at extremely small scales where atoms, electrons, and photons dominate behavior. The framework did not arise for philosophical reasons. It emerged after a series of failures of classical models in the face of increasingly precise experiments. Some phenomena simply refused to follow the familiar smooth rules. During the development of quantum mechanics, one of the central ideas was presented by Werner Heisenberg in 1927, the uncertainty principle. This principle is not about the limits of measuring devices or experimental technique. It is about the limits of nature itself. At its core, certain pairs of physical quantities cannot be known simultaneously with arbitrary precision. The most famous pair is the position and momentum of a particle. The more precisely the position is determined, the more uncertain the momentum becomes, and vice versa. In classical physics, we often imagine that if all motion, all energy, and all particles were removed, what would remain is a perfectly still state. But quantum mechanics begins by breaking precisely that picture. Uncertainty is not the result of humans measuring too clumsily. It does not arise because the act of measurement disturbs the system. Instead, it exists even before any observation takes place. Particles simply do not simultaneously possess exact values for both position and momentum. This alone undermines the idea of absolute rest. For a particle to be truly motionless, it would need to have zero momentum, while also occupying a completely definite position. But quantum mechanics forbids that combination. The more tightly the position of a particle is fixed, the more uncertain its momentum becomes. If the momentum were known to be exactly zero, the particle's position would spread out across space. No clever arrangement or better measuring device can avoid this. It is part of the structure of the quantum world. Thus, at very small scales, complete stillness is not an attainable state. Motion, in some form, always remains. Even when a system falls to its lowest possible energy state, the ground state particles still retain a residual motion. The remaining energy is often called zero-point energy. It is not infinite energy, but a minimum floor, a limit below which energy cannot be reduced. At everyday scales, we hardly notice this. The objects around us contain enormous numbers of particles. The restless motion of individual atoms averages out on large scales. A table therefore appears solid and motionless. A room appears quiet. But at the microscopic level, that motion has never stopped. Its existence produces measurable consequences. Electrons retain motion even in their lowest energy states, which prevents atoms from collapsing. Even at absolute zero temperature, molecules cannot freeze into perfectly motionless structures. Quantum fluctuations prevent absolute stillness. Quantum mechanics therefore does not allow a state of perfect rest. It only allows the lowest possible level of activity. This also changes the meaning of emptiness. Suppose every particle were removed from a region of space. The quantum rules would still remain. The theoretical framework would still exist. And that very framework forbids complete stillness. Here, uncertainty is not human ignorance. It is not about what we do not yet know. It is about the nature of existence itself. A particle does not secretly carry an exact position and momentum waiting to be discovered. Those quantities genuinely remain undefined until an interaction occurs. For a long time, physicists hoped otherwise. Perhaps uncertainty merely reflected missing information. Perhaps deeper variables, hidden variables existed, keeping nature deterministic at a deeper level. But successive experiments ruled out that hope. Tests of quantum correlations, especially those inspired by John Bell's work in the 1960s, showed that no local hidden variable theory can reproduce the observed results. Uncertainty is therefore not a temporary gap in knowledge. It is fundamental, and this has direct consequences for the vacuum. If uncertainty governs all physical systems, then empty space cannot be completely still. Removing particles does not remove all activity. According to quantum mechanics, activity can briefly appear, fluctuate, and then disappear again, always constrained by the uncertainty principle. Of course, this does not mean that anything can happen at any time. The limits are extremely strict. Fluctuations are constrained. Energy is still conserved on average. These effects are usually very subtle, but subtle does not mean non-existent. Once absolute rest is forbidden, complete emptiness cannot be achieved either. There will always remain a baseline level of activity permitted by the rules of the theory. This runs against human intuition. We tend to associate quiet with absence and silence with nothing happening. Quantum mechanics replaces that silence with something more like a whisper too small to notice directly, yet never entirely gone. There is a quiet bit of irony in this. Nature never quite sits still, even after everything has been cleared away. This restlessness does not produce obvious motions or dramatic explosions. It exists on scales far removed from everyday experience, yet its consequences accumulate over time. The uncertainty principle also forces physics to rethink the concept of limits. In classical physics, the question is often what happens when a quantity approaches zero velocity, zero temperature, zero energy. Quantum mechanics replaces zero with minimum, the smallest value allowed to exist, the lowest state that can be reached. That minimum is not an arbitrary number. It emerges directly from the structure of the theory, as fundamental as the conservation laws themselves. By this point, the concept of emptiness has already changed several times. It has gained geometry, fields, and energy, and now it gains something else. Motion that cannot be removed, a baseline level of activity that always remains. Quantum mechanics may not yet tell us exactly what empty space does, but it tells us very clearly what empty space cannot do. It cannot be perfectly still. When quantum mechanics removed the possibility of a perfectly motionless state, the concept of the vacuum also had to change. Empty space could no longer be imagined as a completely still region. It could not be perfectly defined, nor could it be a silent void. If the uncertainty principle forbids absolute stillness, then even the lowest energy state of a system, what physics calls the vacuum, must contain some level of activity. This activity is not chaotic. It has structure, follows rules, and is constrained by very strict limits. But it is real. Once uncertainty was accepted as a fundamental feature of nature, the idea of nothing at all began to face serious pressure. Empty space was no longer the quiet endpoint of everything. It became a dynamic state, controlled, but never completely motionless. And within that faint restlessness, the vacuum gradually revealed its true character. Physicists, therefore, did not abandon the concept of the vacuum. They redefined it. The vacuum no longer meant the absence of everything, but rather the lowest energy state allowed by the laws of nature. This is what is called the quantum vacuum. In everyday language, a vacuum simply means that everything has been removed from a region of space. But in quantum physics, the vacuum is not what remains after everything has been taken away. It is a specific state, the ground state of a system, the configuration with the smallest possible energy but not zero energy. This distinction is crucial. The quantum vacuum is not empty in the classical sense. It is a state of fields rather than the absence of particles. According to quantum field theory, the framework that combines quantum mechanics with the concept of fields, particles are not fundamental objects flying through space. They are merely excitations of underlying fields. An electron is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. The fields exist first. Particles are what happen when energy becomes concentrated within them. This idea gradually took shape in the early 20th century. One of the key figures in its development was Paul Dirac. In attempting to combine quantum mechanics with special relativity, he helped establish the view that fields themselves must also be quantized. Energy at microscopic scales does not vary continuously but appears in discrete amounts. Quantizing a field means that each possible mode of vibration of that field is treated as a quantum system with allowed energy levels, and even the lowest level, the ground state, still carries energy. This is not an arbitrary detail. It follows directly from the uncertainty principle. If a field had exactly zero energy, then both the value of the field and the rate at which it changes would have to be perfectly defined. But quantum mechanics forbids that. The field must therefore fluctuate even in its lowest energy state. From this comes a quiet but profound conclusion. Empty space, if understood as a region with no particles, still contains fields. And those fields, even in their ground state, continue to fluctuate. These fluctuations are extremely small. They do not accumulate into visible motion. Quantum rules keep them within very tight limits. But they exist. For this reason, physicists often describe the quantum vacuum as restless, not chaotic, not violent, but never completely still. Energy may briefly appear in one form and disappear in another, all constrained by the uncertainty principle and conservation laws. Here it is important to be careful with language. Popular explanations often say that particles appear and disappear from nothing. This phrasing is convenient but not entirely accurate. What actually fluctuates are the fields. The picture of particles is simply a way of describing certain interactions. In quantum field theory, the vacuum is the background state of potential activity within the fields, a baseline that is never completely switched off. It is not empty in the sense of total absence. It is only empty in the sense that there are no stable excitations. This distinction helps avoid misunderstanding. Vacuum fluctuations do not violate the conservation of energy. When considered over long periods, energy still balances out. These fluctuations exist only briefly and are tightly constrained. They do not allow free energy to be extracted or matter to be created without cause. Yet the vacuum still leaves observable traces. The lowest energy state of the fields influences how particles behave. It can shift energy levels, modify interactions, and affect the decay rates of particles. This means the vacuum is not a passive background. It participates in physical processes even when nothing appears to be happening. From this point, a subtle shift in questioning occurs. Instead of asking, "What is inside empty space?" physics begins to ask, "What state are the fields in?" Because particles are only manifestations of deeper structures. Beneath them lie fields, entities that cannot be removed without removing the very framework of physics itself. The quantum vacuum is therefore the state the fields reach when they are as quiet as the rules allow them to be. And even that quiet still contains motion. This idea can feel unsettling because it removes the notion of absolute nothingness. There is no switch that can completely turn reality off. There is always at least a faint background hum. Yet that hum is not arbitrary. It is tightly controlled. The vacuum does not erupt with energy, nor does it collapse into chaos. Its fluctuations average out over time, and their consequences are subtle, accumulating slowly but precisely. Perhaps a simple way to imagine it is like the calmest possible lake, yet never perfectly flat. Even when there is no wind, tiny ripples remain. They do not arise from any obvious disturbance. A lake can be calm enough to reflect the sky almost perfectly. But that quiet does not mean the water is completely motionless. It is simply obeying its own natural constraints. The lake may appear still, but it never truly freezes into an absolute state. The quantum vacuum has a similar character. It is not the most silent state one could imagine, but merely the lowest energy state that quantum fields can reach. When this perspective emerged, many older questions in physics began to dissolve naturally. Fields no longer required a classical material medium in order to exist. Light no longer needed an ether to propagate. Electromagnetic waves are simply traveling excitations of the electromagnetic field, a field that exists everywhere that space-time allows. And because those fields are always present, even after removing matter, air, radiation, and heat, emptiness is not truly empty. The fields remain. Their ground state remains. And their smallest fluctuations remain as well. From that point onward, the concept of nothingness became far more precise than ordinary intuition suggests. It was no longer a vague emptiness, but a clearly defined physical state, with measurable properties. At first, all of this existed mainly within the mathematical structure of quantum field theory. But physics never accepts theoretical consistency alone. It always asks the next question. If the vacuum is not completely still, could that faint instability produce something observable? The answer is yes. The vacuum does not exist merely as a conceptual requirement of mathematics. It leaves traces in the physical world. It can modify the forces between systems. It can shift energy levels. Under carefully controlled conditions, these effects can be detected. The vacuum, once defined simply as the lowest energy state of fields, is no longer entirely invisible. Its activity is extremely subtle, but it is still activity. And when that activity is isolated, constrained, or shaped, the vacuum begins to reveal itself. This revelation arises from a basic fact about quantum fields. They can never be perfectly still. Even in their lowest energy state, each field carries a minimal amount of energy called zero-point energy. The uncertainty principle prevents the field from having a perfectly fixed value everywhere. Instead, it always fluctuates slightly around that minimal energy level. These fluctuations are called vacuum fluctuations. They are not explosions in empty space, nor storms of energy. They are simply extremely small and brief variations of energy within the fields. Their size and duration are tightly constrained. The smaller the region of space considered, the larger the energy fluctuation can be. But if a fluctuation lasts longer, its energy must be smaller. These limits are not arbitrary assumptions. They arise directly from the structure of quantum mechanics. As a result, these fluctuations exist only over extremely small distances and extremely short times. At the familiar scales of everyday life, all of these variations average out and nearly disappear. The vacuum, at human scales, appears completely quiet. Sometimes this phenomenon is described using the image of particles appearing and disappearing in empty space. But that wording can be misleading. What actually fluctuates are the fields. Particles are simply a way of describing localized excitations of a field when energy becomes concentrated enough to behave like a discrete unit. In calculations, vacuum fluctuations sometimes resemble fleeting particle pairs. These are often called virtual particles. However, they are not particles in the ordinary sense. They cannot be separated, cannot be detected directly, and cannot be made to persist. They are simply mathematical representations of temporary field excitations during interactions. The important point is not that particles appear from nothing. The important point is that fields fluctuate within strict limits, and those constrained fluctuations can influence measurable physical processes. These fluctuations exist for extremely short durations. They do not last long enough to become independent objects that can be directly observed. They appear only as intermediate effects in interactions. Distance also plays an important role. At extremely small scales, the vacuum becomes slightly restless. But as the region of space considered grows larger, those fluctuations gradually smooth out and cancel. This balance prevents everything from collapsing into chaos. The vacuum is not unstable. It does not collapse, nor does it erupt with energy. The fluctuations exist precisely because they are constrained. Intuition might suggest that nothingness is a place where anything could happen, but quantum mechanics shows the opposite. Even the vacuum follows rules. Within the framework of quantum mechanics, even the smallest fluctuations of the vacuum are not allowed to occur arbitrarily. Total energy is still conserved. Fluctuations are always limited. Causality is not broken. It is precisely these constraints that keep the familiar universe stable. If vacuum fluctuations were unrestricted, matter could not remain stable. Atoms would fall apart. and space itself might tear the structure of reality. The fact that vacuum fluctuations occur only within strict limits is what allows matter to maintain stable forms. The traces of these fluctuations are not seen directly, but they reveal themselves through their influence on measurable quantities. In atoms, the energy levels of electrons do not perfectly match theoretical predictions if the background activity of fields is ignored. Precise measurements show tiny differences that can only be explained when vacuum fluctuations are taken into account. Even when nothing appears to be happening, the fields are quietly active, and that activity subtly changes the way particles interact. Similar effects appear when calculating the forces between charged particles at extremely small distances. The vacuum contributes small corrections to the strength of these forces. Each individual fluctuation is extremely small, but the importance does not lie in the size of any single fluctuation. What matters is the accumulated influence of countless fluctuations across many interactions and over long periods of time. In this way, the vacuum leaves its signature. This emphasizes an important idea: nothingness is not chaos. It is activity constrained at the lowest possible energy level. Vacuum fluctuations do not occur in a disorderly, random way. They follow statistical patterns determined by the underlying theory. There is a quiet regularity to them. The vacuum fluctuates like a tightly stretched surface, trembling very slightly, motions that are rapid and small, but never grow into instability. The system remains stable because the rules constantly push it back toward equilibrium. It is also important to understand what vacuum fluctuations are not. They are not a source of free energy. They cannot be harvested or exploited. They do not violate conservation laws. Ideas suggesting that useful energy could be extracted from the vacuum usually arise from misunderstandings of the phenomenon. The vacuum does not give away energy. It merely responds to boundaries, conditions, and interactions around it. When those conditions change, the vacuum adjusts its state. That adjustment can sometimes produce observable effects, but always within the limits imposed by physical law. This is why experimental verification is essential. Vacuum fluctuations are not accepted simply because they are conceptually appealing. They are accepted because theory predicts precise outcomes that can be tested. Before turning to specific experiments, it is important to recognize how profoundly the concept of emptiness has changed. It is no longer a space where anything might happen. It is a structured state, governed by rules that both allow activity and constrain it. The vacuum therefore becomes something both restless and disciplined, active, yet restrained. This also explains why nothingness is difficult to describe using familiar concepts. It is not exactly an object, but it is not the absence of everything either. It is a state defined by the lowest possible energy and by unavoidable fluctuations. Once this is understood, the next step becomes natural. If vacuum fluctuations can influence forces and energy levels, then, under the right conditions, they must be observable. Not by seeing particles appear and disappear, but by measuring the consequences that emptiness produces. Physics does not require the vacuum to announce itself. It only asks whether the world behaves differently because the vacuum exists. And the answer, repeated quietly through many measurements, is yes. The next task is to isolate those differences to shape emptiness in ways that allow its structure to reveal itself. Vacuum fluctuations explain why such effects exist. Experiments demonstrate that they truly occur. The faint sound of nothingness is not imaginary. It leaves traces. And when those traces are measured, the vacuum ceases to be merely a requirement of theory and becomes an experimental reality. One of the clearest demonstrations of this comes from an effect so subtle yet so precise that it is difficult to deny: the Casimir effect. In the late 1940s, the Dutch physicist Hendrik Casimir was studying quantum fields in confined spaces. He was not searching for a philosophical statement about nothingness. His work concerned practical problems involving electromagnetic forces. Yet from this research emerged a direct prediction about how empty space itself should behave. The conceptual setup of the experiment is remarkably simple. Place two flat, uncharged metal plates parallel to each other and extremely close together, separated by only a tiny gap. Then remove almost all the air so that the region between them becomes a vacuum in the classical sense. According to classical intuition, nothing should happen. No electric charge, no force. Just two neutral objects resting quietly in empty space. Quantum mechanics predicts something different. The electromagnetic field exists everywhere, including within the narrow gap between the plates. Even in its lowest energy state, the field still fluctuates. However, those fluctuations are not completely free. They depend on the boundaries of the space in which they exist. Between the metal plates, only certain patterns of vibration, certain modes of the field are allowed, while many others are excluded by the confinement of the space. Outside the plates, the electromagnetic field has much more freedom. More fluctuation modes are allowed. As a result, the vacuum energy outside the plates is slightly higher than the vacuum energy within the narrow gap between them. This tiny difference produces a force. The two metal plates are pushed toward each other not because something pulls them together, but because the vacuum on the two sides is no longer the same. Empty space outside behaves differently from the empty space confined between the metal surfaces. What makes the Casimir effect remarkable is not its strength. The force is extremely small. It is not enough to bend steel or push objects around a room. But when two surfaces are placed only a few hundred nanometers apart, sufficiently sensitive instruments can still detect it. And at those tiny distances, something unusual appears. The force arises from the very structure of the quantum vacuum. No particles are exchanged. No electric charges interact. The source of the force is simply the way quantum fields exist within a confined region of space. When surfaces create boundaries, geometry begins to play a decisive role. Change the distance, alter the shape or orientation of the boundary plates, and the force changes in predictable ways. The vacuum, it turns out, responds to structure. From that moment on, empty space could no longer be considered a passive backdrop. It has mechanical consequences. It can exert pressure. The Casimir effect has been confirmed many times in laboratories using different materials, geometries, and measurement techniques. Experimental results match theoretical predictions with high precision. This is not an isolated phenomenon. This fact is decisive in a very quiet way. The energy of the vacuum is no longer inferred, only indirectly through atomic energy shifts or theoretical reasoning. It produces a measurable force between macroscopic objects. In other words, empty space can exert pressure. That closed a door that once remained open in physics. Previously, one might have argued that vacuum fluctuations were merely mathematical tools, calculation techniques without independent physical reality. The Casimir effect shows the opposite. The vacuum can perform work. However, it is important to be clear about what this means. The Casimir force does not turn the vacuum into an explosive or unstable energy source. It is a conservative force that depends entirely on configuration. When boundaries change, the effect changes accordingly. The vacuum is not a reservoir of energy waiting to be exploited. It behaves more like a system that responds to the surrounding structure. There is a quiet elegance in that. Emptiness does not loudly demand attention. It reveals itself only when constrained. Two metal plates placed close together are enough to make an otherwise invisible structure of space become apparent. This echoes a familiar principle in physics. When geometry changes, the behavior of space changes with it. Curvature influences motion. Boundaries modify fields. Structure always matters. The Casimir effect also serves as a bridge between scales. In laboratories, it is observed using extremely precise instruments under carefully controlled conditions. But the principles behind it are not limited to laboratory settings. They apply wherever quantum fields exist, which means everywhere. If geometry can alter the behavior of the vacuum between two metal plates, then in principle it can do the same near stars, inside cavities of space, or across cosmic distances. The physical rules remain the same, only the scale changes. The Casimir effect does not directly explain those large cosmic phenomena, but it establishes something essential. Vacuum energy is not philosophical speculation. It produces measurable forces. From that point on, the way we speak about empty space must change. It is no longer merely the gap between objects. It reacts. It exerts influence when geometric conditions demand it. This story also reveals a subtle lesson about how physics progresses. The Casimir effect was not discovered through dramatic phenomena. It emerged from careful attention to constraints, symmetries, and the internal consistency of theory. The vacuum revealed itself not through spectacle, but through precision. Over time, the concept of emptiness accumulated more and more roles. Space carries geometry. It contains fields. It stores energy. It fluctuates. And under certain conditions, it can produce force. Laboratory confirmation of vacuum energy anchored decades of theoretical work to a measurable reality. The quiet fluctuations of the quantum vacuum are no longer an abstract idea. They leave traces that instruments can detect. And once that is accepted, the question naturally expands. If vacuum energy exists between two metal plates in a laboratory, then it exists everywhere in the universe, not necessarily in the same form or producing the same effects, but still as a property of space itself. In modern physics, this concept has a clear definition. Vacuum energy is the energy of the lowest state that quantum fields can reach, even when no particles are present. Each field has its own modes of vibration, and each mode carries a minimal amount of energy. When all contributions from all fields and all possible modes are added together, the result is a non-zero energy associated with empty space itself. That is vacuum energy. It is not fuel. It is not energy stored in particles waiting to be released. It is simply a background property of the fields that constitute physical reality. At very small scales, this property reveals itself through effects such as the Casimir force and through subtle shifts in the behavior of atoms. At laboratory distances, the story seems fairly clear. The effects of vacuum energy are predicted by quantum field theory and observed in experiments. The calculations are far from simple, but the final results match what instruments measure. The real difficulty appears only when our view expands to the largest scale imaginable, the scale of the universe. In general relativity, energy is not just an abstract number. It curves space-time. Any form of energy has gravitational consequences, not only matter or radiation, but also the energy of empty space itself. If the vacuum carries energy, then in principle it must influence how the universe expands. When physicists attempt to calculate that energy density using quantum field theory, they obtain a startling result, a value that is enormous. Even the most conservative estimates produce numbers so large that, if taken literally, they would curve space-time violently. The universe would either collapse almost instantly or expand so wildly that galaxies would never have had a chance to form. But the observed sky tells a completely different story. The expansion of the universe, on large scales, proceeds rather gently. Galaxies form. Stars persist for billions of years. Space does not tear itself apart. If vacuum energy exists, its gravitational influence is vastly smaller than what straightforward quantum calculations predict. The immense gap between these two results is known as the vacuum energy problem, sometimes also called the cosmological constant problem. This is not a minor discrepancy in measurement. It is one of the largest disagreements between theory and observation in all of physics. The way the problem is stated is actually very simple. Quantum field theory predicts an enormous vacuum energy. Cosmological observations indicate an extremely small value. Both theoretical frameworks work extraordinarily well in their own domains, but when placed side by side, they contradict each other. The natural temptation is to rush towards solutions. Perhaps nearly perfect cancellations occur between different energy contributions. Perhaps new particles exist, new symmetries yet to be discovered, or unusual mechanisms in the structure of space-time. Some hypotheses suggest that only differences in vacuum energy have gravitational significance. Others question whether gravity responds to vacuum energy in the same way it responds to other forms of energy. So far, no idea has reached consensus. What is striking here is not the solution but the existence of the problem itself. Vacuum energy is real enough that it must be explained, yet subtle enough to resist every simple interpretation. This tension reveals something important about emptiness. Empty space is not a blank surface where theory and observation automatically agree. It is the place where the deepest principles of physics meet, and where they have not yet been fully reconciled. There is also a lesson here about scale. At laboratory distances, vacuum energy behaves exactly as quantum field theory predicts, but at cosmic scales, its role becomes mysterious. The same concept behaves differently depending on context. That does not mean one scale is correct and the other wrong. It suggests that understanding emptiness requires theoretical frameworks capable of spanning an enormous range of sizes from subatomic distances to the scale of the observable universe. Sometimes physicists refer to this problem as an embarrassment, but that description hides something more positive. It marks the boundary of current understanding. It shows where theory remains incomplete. Importantly, the problem does not arise from measurement errors. Astronomical observations are consistent and precise, nor is it a failure of quantum mechanics. At small scales, the framework continues to predict countless phenomena correctly. The real difficulty lies in bringing the two worlds together. At that intersection, the concept of vacuum energy stands quietly. It connects quantum fields with the curvature of space-time. It links the smallest fluctuations to the largest structure of the universe. And once again, emptiness proves not to be simple. It is not what remains after everything else has been removed. It is an active component of physical reality. Up to this point, physics has not yet assembled all the pieces of this story into a complete picture. But that uncertainty is not something that needs to be hidden. It is simply the reality of science. There is a certain calmness in admitting that nature is not required to be simple at every level. Understanding advances step by step, and sometimes questions persist for a long time, simply because they sit at the edge of what current theories can handle. Vacuum energy is one of the concepts that lives at that boundary. It is real enough that physicists must take it into account, yet elusive enough that it has not been fully explained. This tension does not weaken the idea of energy and emptiness. On the contrary, it deepens it. It suggests that empty space is woven into the structure of the universe in ways we still do not completely see. When our attention turns away from laboratory instruments and toward the sky, a natural question arises. If vacuum energy exists everywhere, even if its local influence is very small, what role does it play in the formation and evolution of the entire universe? That question belongs to cosmology. And at the largest scales imaginable, emptiness takes on yet another unexpected role. Once we accept that empty space can carry energy, possess structure, and obey physical laws, space is no longer a static container holding galaxies. It becomes something that can change. And the most important way it changes is through expansion. The common picture of cosmic expansion often suggests an explosion, fragments flying outward into a fixed background of space. This image is familiar, but it is misleading. In reality, the expansion of the universe is not primarily about galaxies rushing through space. Space itself is stretching. The distance between galaxies increases not because they actively move away, but because the space between them gradually grows larger. Two galaxies may remain almost stationary relative to their local surroundings, yet over time they still drift apart. The reason is simple. The ruler used to measure distance space itself is changing. This idea was not always obvious. At the beginning of the 20th century, astronomers were still debating whether the distant nebulae seen in the sky belonged to the Milky Way or were separate galaxies. Cosmic distances had not yet been firmly established. Observations were still limited. The turning point came from the work of Edwin Hubble. Working with the telescope at the Mount Wilson Observatory in California, he studied light from distant galaxies and compared their observed brightness with known properties of certain types of stars. In this way, he could estimate their distances. He then compared those distances with the way the light from those galaxies was shifted toward longer wavelengths. The result appeared with surprising simplicity. The farther a galaxy is, the more its light is shifted. This indicates that distant galaxies are moving away from us faster than nearby ones. The relationship was not random, it followed a clear and proportional pattern. The conclusion was almost unavoidable. On large scales, the universe is expanding. What matters is how this expansion is understood. No galaxy is fleeing from a central point in the universe. In fact, there is no center at all. Any location in the universe would observe distant galaxies receding in every direction. This is exactly what would happen if space itself was stretching uniformly. This stretching occurs everywhere, even in regions that appear almost completely empty. In fact, it becomes most visible there. Dense structures such as galaxies and galaxy clusters are held together by gravity and internal forces, so they resist expansion. But vast regions that contain almost no matter have nothing to oppose the stretching of space. Cosmic voids, immense empty regions of the universe, therefore expand along with space itself. No force inside them is pushing matter outward. There is simply nothing present to resist the stretching. This represents an important shift in perspective. Expansion does not require matter to move or act. It only requires space to evolve over time. Even a region completely devoid of particles will grow larger as the universe expands, and this behavior emerges directly from the equations of general relativity. In the equations of general relativity, space is not a fixed stage. Its geometry can change over time. Depending on how energy and curvature are distributed, those equations allow universes that expand or contract. What Edwin Hubble observed was not the cause of expansion. It was simply evidence that expansion was already built into the structure of space-time. The galaxies, by drifting apart, inadvertently revealed it. Scale plays a decisive role in this story. At small distances, expansion is almost non-existent. The spacing between atoms in a table does not increase. The solar system does not expand. Even galaxies themselves remain bound by gravity. Local forces completely dominate at these scales. At larger scales, the picture begins to change. Galaxy clusters still form and remain bound through gravity, but the clusters themselves gradually move farther apart. And at the largest distances in the universe, expansion becomes the dominant effect. This dependence on scale allows two seemingly contradictory facts to coexist. The universe can expand while stars, planets, and life remain stable. Cosmic expansion is not a tearing force. It is a slow, stretching process that only becomes significant across sufficiently large distances. This also explains why emptiness is so important. Most of the volume of the universe is not filled with matter. It consists of enormous regions with extremely low density. These regions reflect the expansion of space most clearly. Matter tends to resist, distort, and complicate the process. Empty space stretches freely. Of course, this does not mean expansion originates only from emptiness. The expansion rate of the universe depends on its total energy content, including matter, radiation, and any other components that contribute to the curvature of space-time. But the emptiest regions are where the expansion becomes most visible. There is a subtle conceptual shift here. Instead of imagining objects moving away through space, we begin to understand that space itself is changing. Distance itself is evolving. This idea may sound abstract, but it leaves observable traces. When light travels through expanding space, its wavelength is stretched along with it. This is why light from distant galaxies is redshifted. The light does not lose energy because of friction or resistance. The space through which it travels has simply changed. Even the emptiest regions of the universe participate in this process. A photon crossing a cosmic void experiences the same stretching as when it travels through regions rich with matter. Emptiness does not shield space from its own evolution. By this point, empty space has accumulated an astonishing list of responsibilities. It carries geometry, it contains fields, it stores energy, it fluctuates, it produces forces between metal plates, and at the largest scale imaginable, it stretches slowly and persistently. But the story contains one more twist. For most of the 20th century, scientists believed that the expansion of the universe would eventually slow down. The gravitational pull of matter, they reasoned, should act as a cosmic brake. Matter attracts matter. Over time, that attraction should gradually reduce the expansion rate. The universe might collapse again, expand forever, or reach some balanced state, but a slowing expansion seemed natural. This expectation was entirely reasonable. It followed directly from general relativity and from how matter behaves under gravity. Then observations began telling a different story. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, began measuring the expansion history of the universe with unprecedented precision. Their tool was a special type of stellar explosion, type Ia supernovae. These explosions are extremely useful because they follow a remarkably consistent brightness pattern. When a white dwarf star reaches a critical mass and explodes, the brightness of the explosion evolves in a very predictable way. This makes them reliable cosmic distance markers. By comparing their observed brightness with their known intrinsic brightness, astronomers can determine how far away they are. The two teams observed supernovae in distant galaxies, looking back billions of years into the universe's history. They measured their distances and also measured the redshift of their light, allowing them to reconstruct how fast the universe was expanding at different times. The initial expectation was clear. If expansion has been slowing over time, then distant supernovae, representing the earlier universe, should appear brighter than predicted by a universe expanding at a constant rate, because the universe would have been expanding faster in the past and then gradually slowing down. But the observations did not show that. There was a moment in the history of cosmology when the data began to tell a story completely different from what intuition had suggested. Very distant supernova explosions used as standard candles to measure cosmic distances appeared dimmer than predicted. At first, it was only a puzzling detail, but as more measurements accumulated, the anomaly repeated itself consistently. Two independent research teams, using different analysis methods, arrived at the same conclusion. The universe was not slowing down under the pull of gravity. Instead, its expansion was accelerating. For that to happen, something must exist that acts opposite to gravity on the largest scales of the universe. It does not clump into galaxies, nor collapse into familiar structures of matter, yet it influences the way space itself expands. Scientists gave it a rather modest name, dark energy. The name does not claim to explain what it is. It simply describes the observed effect, the phenomenon that is causing the expansion of the universe to accelerate. What makes dark energy unusual is where it appears to exist. It does not concentrate in dense regions of matter such as galaxies or galaxy clusters. Instead, its influence appears evenly distributed throughout space. This behavior leads physicists to treat it as a property of space itself. As the universe expands, the total amount of dark energy increases, not because more of it is created, but because there is more space for it to inhabit. Remarkably, its energy density remains almost unchanged even as space grows larger. This persistence is completely different from the way matter and radiation behave. As space expands, matter becomes more diluted and radiation spreads out as well. Dark energy, however, does not fade away. It maintains nearly the same density. This suggests a deep connection between dark energy and the vacuum of space with emptiness itself. What we know comes from several independent sources of evidence: supernova observations, measurements of the cosmic microwave background, and surveys of the large-scale structure of the universe. All point to the same picture. The universe's expansion is accelerating, yet the true nature of dark energy remains uncertain. One possibility is that it corresponds to the cosmological constant that Einstein once added to the equations of general relativity, implying that empty space itself possesses intrinsic energy. Other ideas propose slowly evolving energy fields or even modifications to gravity on cosmic scales. So far, no hypothesis has been confirmed. In cosmology, the guiding principle is clear: data comes first, and theory must follow. And the data has revealed one simple fact: the universe is accelerating. If dark energy is indeed a property of space itself, the implications become profound. Most of the universe's volume is empty space, Galaxies and clusters occupy only a tiny fraction of it. This means that on the largest scales, emptiness becomes the dominant factor shaping the behavior of the universe. Matter still forms local structures. It creates stars, galaxies, and familiar chemical processes. But for the overall evolution of the cosmos, control appears to belong to empty space. This reverses a long-standing intuition. Historically, emptiness was viewed as absence, the remainder after everything else had been removed. In modern cosmology, emptiness becomes a central actor. The acceleration itself is extremely gentle. It does not tear apart galaxies or disrupt gravitationally bound systems. On local scales, everything remains stable. Only across billions of years and immense cosmic distances does the change become apparent. The universe is not exploding violently. It is simply stretching a little faster over time. Dark energy is not a violent force pushing objects apart. It changes the expansion rate of space itself. Because of this, cosmic structures remain stable, while the long-term future of the universe gradually unfolds. At this point, an intriguing connection appears. The concept of energy associated with the vacuum, once studied in delicate laboratory experiments, now enters the story of cosmic expansion. The two phenomena are not necessarily identical in mechanism. Caution is necessary, but the conceptual link is difficult to ignore. The energy of empty space may leave its imprint on every scale, and like many great discoveries in science, this mystery did not arise from a dramatic event. It emerged from a small detail. The universe did not behave the way we expected. The gravitational slowdown never appeared. Once again, emptiness did not announce itself loudly. It simply refused to behave as we once believed it would. And from that quiet refusal, the emptiness of the universe gradually emerged as the dominant component of its energy budget, silently shaping the past, present, and future of cosmic expansion. There was a moment in the history of cosmology when the data began to tell a story completely different from what intuition had suggested. Very distant supernova explosions used as standard candles to measure cosmic distances appeared dimmer than predicted. At first, it was only a puzzling detail, but as more measurements accumulated, the anomaly repeated itself consistently. Two independent research teams, using different analysis methods, arrived at the same conclusion. The universe was not slowing down under the pull of gravity. Instead, its expansion was accelerating. For that to happen, something must exist that acts opposite to gravity on the largest scales of the universe. It does not clump into galaxies nor collapse into familiar structures of matter, yet it influences the way space itself expands. Scientists gave it a rather modest name: dark energy. The name does not claim to explain what it is. It simply describes the observed effect, the phenomenon that is causing the expansion of the universe to accelerate. What makes dark energy unusual is where it appears to exist. It does not concentrate in dense regions of matter such as galaxies or galaxy clusters. Instead, its influence appears evenly distributed throughout space. This behavior leads physicists to treat it as a property of space itself. As the universe expands, the total amount of dark energy increases not because more of it is created, but because there is more space for it to inhabit. Remarkably, its energy density remains almost unchanged even as space grows larger. This persistence is completely different from the way matter and radiation behave. As space expands, matter becomes more diluted, and radiation spreads out as well. Dark energy, however, does not fade away. It maintains nearly the same density. This suggests a deep connection between dark energy and the vacuum of space with emptiness itself. What we know comes from several independent sources of evidence: supernova observations, measurements of the cosmic microwave background, and surveys of the large-scale structure of the universe. All point to the same picture. The universe's expansion is accelerating. Yet the true nature of dark energy remains uncertain. One possibility is that it corresponds to the cosmological constant that Einstein once added to the equations of general relativity, implying that empty space itself possesses intrinsic energy. Other ideas propose slowly evolving energy fields or even modifications to gravity on cosmic scales. So far, no hypothesis has been confirmed. In cosmology, the guiding principle is clear. Data comes first, and theory must follow. And the data has revealed one simple fact: the universe is accelerating. If dark energy is indeed a property of space itself, the implications become profound. Most of the universe's volume is empty space. Galaxies and clusters occupy only a tiny fraction of it. This means that on the largest scales, emptiness becomes the dominant factor shaping the behavior of the universe. Matter still forms local structures. It creates stars, galaxies, and familiar chemical processes. But for the overall evolution of the cosmos, control appears to belong to empty space. This reverses a long-standing intuition. Historically, emptiness was viewed as absence, the remainder, after everything else had been removed. In modern cosmology, emptiness becomes a central actor. The acceleration itself is extremely gentle. It does not tear apart galaxies or disrupt gravitationally bound systems. On local scales, everything remains stable. Only across billions of years and immense cosmic distances does the change become apparent. The universe is not exploding violently. It is simply stretching a little faster over time. Dark energy is not a violent force pushing objects apart. It changes the expansion rate of space itself. Because of this, cosmic structures remain stable, while the long-term future of the universe gradually unfolds. At this point, an intriguing connection appears. The concept of energy associated with the vacuum, once studied in delicate laboratory experiments, now enters the story of cosmic expansion. The two phenomena are not necessarily identical in mechanism. Caution is necessary, but the conceptual link is difficult to ignore. The energy of empty space may leave its imprint on every scale. And like many great discoveries in science, this mystery did not arise from a dramatic event. It emerged from a small detail. The universe did not behave the way we expected. The gravitational slowdown never appeared. Once again, emptiness did not announce itself loudly. It simply refused to behave as we once believed it would. And from that quiet refusal, the emptiness of the universe gradually emerged as the dominant component of its energy budget, silently shaping the past, present, and future of cosmic expansion. Empty space, once imagined as a lifeless void, now quietly appears to be the main engine driving the entire story of the universe. It is what stretches space-time faster and faster, and once we recognize that, a fundamental question inevitably returns. If emptiness governs the fate of the cosmos so profoundly, then understanding its nature is no longer a peripheral issue. It becomes central. From there, a thought arises almost naturally. If empty space carries energy, and if that energy is driving the accelerating expansion of the universe, could vacuum energy, the energy predicted by quantum field theory, be the same as the dark energy astronomers observe? The short answer is tempting. Perhaps they are closely related, but the more careful answer is that they have not been proven to be the same, and the gap between the two ideas is far from small. At first glance, the resemblance is difficult to ignore. Both are not tied to matter or radiation, but arise from space itself. Both appear to be distributed uniformly throughout the universe, not diluted as space expands. And most importantly, both curve the geometry of space-time in a similar way, pushing things apart. The simplest and most elegant idea therefore becomes very attractive. Dark energy might simply be vacuum energy, expressed on cosmic scales. In Einstein's equations, it would appear as the cosmological constant, a constant energy of space that drives ever faster expansion. The image is strikingly beautiful, a microscopic phenomenon, once measured in laboratory experiments using closely spaced metal plates, determining the fate of the entire universe. Yet beauty cannot substitute for evidence, and the greatest obstacle lies in the numbers. When physicists calculate vacuum energy using quantum field theory, the predicted value is enormously larger, by dozens or even hundreds of orders of magnitude, than the amount of dark energy allowed by cosmological observations. This is not a small mismatch, not a factor of 10 or 100. It is one of the largest discrepancies modern physics has ever encountered. If the two were truly the same, there would have to exist some unknown mechanism that almost perfectly cancels the gravitational effect of vacuum energy, leaving behind only a tiny remainder, the piece we observe as dark energy. But no such mechanism has yet gained broad acceptance. There are deeper differences as well. Vacuum energy arises naturally and inevitably from quantum fields. It is a theoretical foundation that cannot easily be removed. Dark energy, in contrast, is defined entirely from observation. It is whatever causes the universe's expansion to accelerate. Some models allow it to evolve slowly over time. Current observations are consistent with a constant value, but they do not completely rule out mild changes. Vacuum energy, as calculated in theory, is usually strictly constant. Another intriguing possibility remains, though it is unproven. Perhaps vacuum energy interacts with gravity in an unusual way, different from every other form of energy described by general relativity. Because of these uncertainties, physicists choose their words carefully. They do not simply declare dark energy to be vacuum energy. Instead, they describe dark energy as the cause of cosmic acceleration, a phenomenon firmly supported by observation. Identifying it with vacuum energy remains an interpretation, a beautiful hypothesis, but still provisional. This caution is not hesitation without reason. It reflects lessons learned throughout the history of science. Many ideas once seemed obvious and natural, only to reveal hidden flaws when examined more carefully. Physics advances precisely because it separates what is observed from how we interpret it. Accelerated expansion is a fact. Dark energy is an effective description of that fact. Whether it truly is vacuum energy remains an open question, but the story is still being written. Many scientists believe that identifying dark energy with vacuum energy would be the most natural and economical explanation available. It would not require introducing entirely new entities, only the ingredients already present in quantum field theory and general relativity. Yet natural explanations are not always correct. History has shown that concepts once thought inevitable can later be replaced, just as the old idea of absolute space eventually gave way to a deeper understanding of space-time itself. Looking back through history, we see many ideas that once seemed indispensable ideas whose elegance felt almost irresistible later discarded because of fundamental flaws. The ether is a familiar example. For a time it appeared unavoidable, a graceful explanation for how light might travel through space. Yet careful experiments revealed that it simply was not there. That memory reminds us to remain restrained. The overlap between vacuum energy and dark energy is undeniably suggestive, but it is not yet enough for a definitive conclusion. The differences remain, unresolved and persistent, and perhaps it is precisely this difficulty that hints at something much deeper. The vacuum energy problem is not merely an unreasonable number. It is the clearest expression of the tension between the two greatest foundations of modern physics, quantum mechanics and gravity. Each works remarkably well in its own domain: quantum theory in the microscopic world, gravity across enormous cosmic scales. But when we attempt to combine them, the pieces do not quite fit. Dark energy sits exactly at that intersection, where the two frameworks meet before they are fully prepared to do so. Asking whether the two are identical may simply be too early. It is possible that neither vacuum energy nor dark energy is yet fully understood, either separately or together. The correct theoretical framework may still require concepts that have not yet appeared. But that uncertainty does not weaken what has already been discovered. In fact, it sharpens it. We now know with confidence that emptiness is not nothingness. It has structure. It carries energy. It participates directly in shaping the fate of the universe, curving gravity, driving accelerated expansion, and resisting every attempt to reduce it to something simple. The open question is not whether emptiness matters, but how it matters. And within that uncertainty lies a quiet honesty. Physics does not demand that every mystery be solved immediately in order to progress. It only requires clarity about what is known, what is inferred from evidence, and what still lies beyond reach. At present, vacuum energy and dark energy share a conceptual overlap, but they are not yet identical. They may be two perspectives on the same reality, one emerging from microscopic laboratory physics, the other from large-scale observations of the cosmos. Or they may be related through mechanisms that remain undiscovered. Either way, one fact is clear: empty space is not inert. It participates in the unfolding story of the universe in ways we can measure. The temptation to declare a final answer is deeply human, but restraint protects accuracy. The absence of a solution is not failure, it is simply an honest marker of where our understanding currently stops. And when we look toward those boundaries, the question of emptiness shifts. It is no longer only about what space itself is doing, but about what our present theories can and cannot explain. The greatest challenge lies in how we detect it. Emptiness does not glow. It does not introduce itself directly. We recognize it only through indirect traces, through the motion of galaxies, through the tiny Casimir force between metal plates, through the steadily accelerating expansion of the universe. Every observation must travel a long path. Light from billions of years ago carries the imprint of matter, gravity, and the stretching of space along its journey. To isolate the contribution of emptiness, we rely on complex models and careful assumptions. Even in laboratories, probing the vacuum pushes technology to its limits. The effects are so small that they demand extreme precision. Background noise, material imperfections, and temperature must all be controlled with extraordinary care. These experiments confirm that the vacuum has structure and energy, but they still touch only the surface of its true complexity. And there are deeper theoretical limits as well. Quantum field theory predicts phenomena with remarkable accuracy at the energies we can access. General relativity describes large-scale space-time with equal success. But when emptiness is placed at their intersection, especially near the Planck scale, where lengths are smaller than familiar scales, by 35 orders of magnitude, both theories begin to lose their predictive power. Quantum fluctuations of space-time itself may dominate there, yet no complete theory currently describes them. That is where the true frontier lies, not in the empty regions of the universe, but in the gaps within our own understanding. This is not the moment to lament insufficient effort. It is the moment to acknowledge a real boundary. We cannot yet reach the smallest scales suggested by theory. No experiment can approach the Planck scale, and so every speculation, no matter how refined, remains speculation. Elegant on paper, perhaps, but not yet tested by reality. The observable universe places limits of its own. It has a finite age and a finite size. Light from the earliest moments has only had time to travel a certain distance. Beyond that horizon, whatever emptiness may be doing, curving, fluctuating, or remaining silent, we cannot know. Even within the observable region, fundamental questions remain suspended. Is vacuum energy truly constant in time? Will dark energy forever maintain the same density? Does space-time possess a smallest unit with physical meaning? Mathematics can express such ideas with precision, but experiments have not yet delivered a final verdict. Physics does not hide these gaps. On the contrary, it treats them with almost reverent care. Genuine science carefully distinguishes between what is directly measured, what is inferred from evidence, and what remains hypothetical. Confusing these layers easily creates an illusion of certainty. Restraint, sometimes uncomfortable, becomes a safeguard. The temptation to close the story of emptiness is strong, especially now that it has become so central. But explanation must follow evidence, never run ahead of it. History has taught us this lesson repeatedly. Absolute space was once believed to be an unshakable foundation. The ether once seemed a necessary medium for light waves. Classical emptiness was once imagined as a perfectly empty void. Each of these ideas appeared complete until new evidence forced them to change or disappear. Recognizing today's limits is how we avoid repeating those mistakes. Moreover, emptiness operates across an immense range of scales. On large scales, it appears smooth, uniform, and calm. On small scales, it may swirl with intense fluctuations. Extrapolating carelessly from one scale to another can easily produce serious errors, yet this does not mean progress has stopped. On the contrary, The boundaries of knowledge are often the most fertile places in science. They inspire new experiments, motivate new theories, and sharpen questions in ways that routine answers never could. What we already know, though incomplete, is significant. Emptiness carries its own geometry, contains quantum fields, fluctuates continuously, and genuinely drives the expansion of the universe. Each of these statements is supported by evidence from the Casimir force measured in laboratories to the accelerating motion of distant galaxies. How these properties ultimately emerge from a deeper theoretical framework remains open territory. There is a quiet discipline in accepting this. Science does not promise immediate completeness. It promises reliability within clearly stated limits. Uncertainty, therefore, is not a weakness, it is a defining feature of honest inquiry. It marks the boundary where understanding is still forming, by openly acknowledging what cannot yet be measured. Because of this discipline, physics preserves its credibility. It does not overreach, it avoids complacency, and it leaves room for future discoveries to reshape the picture without contradiction. When ideas gradually converge, these limits do not close the story, they keep it open, allowing refinement. What emerges is not a final answer about emptiness, but a layered understanding. Emptiness is not nothingness. It has structure, it carries energy, it exerts profound influence, yet its map is still incomplete. The remaining uncertainty does not erase what has been discovered, it simply places those discoveries within a clearer frame. With that frame, we can step back and see the larger picture, without pretending to know every detail. The quiet boundaries of measurement are not an ending. They are the context that keeps knowledge honest. From here, the task is not to fill every gap prematurely, but to weave the pieces already revealed into a coherent picture, while leaving room for genuine mystery. Recognizing where the mystery lies is itself a form of deep understanding. And now we can return to the original question, but with far greater care. Is empty space truly empty? In everyday language, empty means complete absence, no objects, no motion, no substance. That definition works well enough in daily life. But under the careful scrutiny of physics, it quickly proves inadequate. Empty space, it turns out, has never been truly empty in the way we once imagined. In Newton's world, empty space was nothing more than a silent stage. Remove all matter, and what remained seemed insignificant. It did not resist motion, store energy, or influence outcomes. That picture proved enormously successful. It allowed planetary orbits to be predicted with remarkable accuracy, and remains the foundation for most engineering and practical calculations today. For many purposes, treating emptiness as nothing at all is still an excellent approximation. Then relativity changed everything. Special relativity fused space and time into a single entity, space-time, and even in the absence of matter, its structure imposes strict limits. The speed of light becomes a universal boundary that all motion must obey. General relativity goes further still. It reveals that space-time can bend, ripple, and evolve over time. Gravity is no longer a force acting through space, it is the shape of space itself. Even empty regions can carry curvature. Gravitational waves can travel through particle-free space. Time can flow at different rates depending on location, even where no matter is present. Then quantum mechanics entered the picture, and emptiness could no longer remain perfectly quiet. The uncertainty principle states that no system can reach a state of complete rest. Even the lowest energy state contains subtle motion. Quantum field theory makes this unavoidable. Fields exist everywhere in space-time. Particles are merely localized excitations of those fields. Removing all particles does not remove the fields themselves. The ground state, the quantum vacuum, remains, fluctuating quietly. Not chaotic nothingness, but the calmest state the laws of physics allow. Local, fleeting fluctuations that strictly obey energy conservation, yet are strong enough to produce measurable effects such as the Casimir force, confirmed in laboratory experiments. And then, on the largest scales imaginable, emptiness emerges as a central actor. The expansion of the universe, is not primarily caused by matter flying outward. Space itself stretches. This process unfolds most freely in regions almost devoid of matter. Observations show that this expansion is accelerating, and the cause called dark energy behaves like a property of space itself. It does not clump, it does not dilute as the universe expands, and today it dominates the cosmic energy budget. From a silent background, emptiness has become a factor shaping the future of the universe. Yet the picture is still incomplete. The relationship between vacuum energy and dark energy remains mysterious. Theoretical calculations and cosmological observations differ by many orders of magnitude. The behavior of space-time at the smallest scales remains beyond our reach. The limits of current theory are clear. There is no single final answer to what emptiness truly is. Its meaning depends on context, on the scale from which we observe it. At everyday scales, an unfurnished room still feels empty. The sky between the stars still appears dark and quiet. The classical approximation treating space as a harmless background works perfectly well. At atomic scales, emptiness reveals the structure of quantum fields and the rules of uncertainty. At cosmic scales, it drives expansion and shapes the universe's fate. Each layer of description is correct within its own domain. None alone tells the whole story. Physics does not erase older pictures and replace them entirely with new ones. Instead, it layers them. Earlier models are limited, refined, and placed into their proper contexts. Emptiness, once imagined as pure nothingness, has become one of the most dynamic concepts in science. It carries geometry, contains energy, fluctuates subtly, and exerts far-reaching influence all quietly, without spectacle, revealing itself only under careful examination. What we already know is remarkable. Empty space is not nothing. It has structure. It participates in physical laws. It shapes motion, time, and cosmic expansion. What remains unknown is equally important. How quantum fields and gravity truly merge, why vacuum energy appears so small on cosmic scales, and what emptiness ultimately looks like at the Planck scale. These are not failures, they are frontiers. So is empty space truly empty? In the simplest everyday sense, yes. In the deeper physical sense uncovered by centuries of study, no. It is calm, but not nothingness. Silent, but not passive. Simple on the surface, yet layered with hidden complexity. Understanding that difference does not require awe or alarm. It only requires patience and perhaps a willingness to accept that nothing at all may be far richer and more alive than its quiet appearance suggests. The exploration of emptiness does not end with a sudden moment of revelation. It ends with a calmer perspective. What once seemed to be mere absence, when examined patiently and carefully, turns out to be a quiet but essential participant in the workings of the universe. And even at the most familiar scale, when we look at an empty room or the dark space between the stars, the classical approximation still holds its value. Emptiness behaves exactly as we expect it to, well enough for everyday life and technology to continue running smoothly. If we did not have that simple way of seeing things, most engineering, satellite navigation, and the technologies we use every day would not be able to function. Yet physics has revealed that this simplicity holds true only within a certain range. Space is not a lifeless box that merely contains things. Relativity showed that space and time are woven together into a single entity space-time whose geometry can be measured. Even when all matter is stripped away, it retains its own structure. It sets the speed limit of light, shapes all motion, bends and expands in response to energy and mass, and those curvatures remain quietly present, even in regions that appear empty. Quantum mechanics adds a deeper layer. A state of absolute stillness is forbidden. Fields exist everywhere, and space-time allows them to exist. They are never permitted to fall completely silent. Even the lowest energy state still trembles faintly, constrained yet impossible to eliminate. When we remove all particles, what is revealed is not nothingness, but a foundational whisper, a disciplined hum, not chaotic, not threatening stability, only quietly obeying quantum law, Its effects are subtle, yet entirely real, measurable, predictable, and testable. In the laboratory, the Casimir force has shown this clearly. Emptiness responds to geometry. Simply change the boundaries, and the vacuum immediately adjusts, producing a force that can be measured. It pushes back, not dramatically, but firmly. On the largest scales, emptiness takes on a role no one once dared imagine. Space itself expands, without needing matter to push outward, and it expands most freely, where there is almost nothing. Observations show that this expansion is accelerating, driven by something that behaves exactly like an intrinsic property of space. Dark energy, whatever its ultimate nature may be, affirms one undeniable fact: the long-term fate of the universe is governed not by what fills space, but by space itself. Emptiness has moved from the margins to become a central actor. Of course, we do not yet understand every detail. The relationship between vacuum energy and dark energy remains unresolved. The behavior of space-time at the smallest scales is still unknown. Our current theories are powerful, but they do not yet form a complete picture. Yet that uncertainty is not frightening. It is entirely normal, a clear sign of the boundary between what is firmly established and what science is still pursuing. What has already been discovered is remarkable. Emptiness has structure, possesses geometry, contains fields, stores energy, fluctuates beneath the surface, and profoundly influences motion, the flow of time, and the expansion of the universe. None of this is mere speculation. It is built solidly on observation, experiment, and theory working together. At the same time, emptiness has never been loud. It does not introduce itself or demand the spotlight. It operates calmly, consistently, revealing its nature only when we take the trouble to look closely. Its influence is gentle, cumulative, and patient. And that is precisely what brings a deep sense of comfort. The universe does not rest on hidden chaos or dramatic forces lurking in the void. It rests on quiet rules applied everywhere, even where there seems to be nothing at all. The idea of absolute nothingness may be beautiful in philosophy, but physical reality does not allow a state in which everything simply switches off. Instead, nature permits only a minimum, a peaceful foundation that still preserves structure and potential within itself. Seen this way, emptiness is not dangerous, unstable, or threatening to swallow matter or dissolve structure. It coexists harmoniously with stars, galaxies, and life itself in a stable balance. Understanding it this way also helps restore a proper sense of scale. Human intuition was formed within a narrow range. Physics carefully extends it step by step, not erasing it, but adding context. Classical approximations remain perfectly valid where they apply. Relativity and quantum theory only refine the picture where refinement is needed. Then the universe becomes not more mysterious, but clearer. Complexity replaces vagueness, structure replaces absence, and questions replace blind assumptions. The universe never empties itself completely. It only settles into the lowest energy states that the laws of nature allow, expands where it can, fluctuates where it must, and follows consistent rules across all scales even when those rules challenge intuition. There is no need to turn curiosity into anxiety or wonder into unease. Emptiness is not a joke or a paradox. It is simply more than it appears. And when we take the time to observe it carefully, without rushing to conclusions, a more peaceful understanding emerges. The universe is not built on nothingness. It is built on a resilient structure that remains even when all things are absent. Empty space was never truly completely empty, and it is precisely that quiet persistence that allows everything else from stars to ourselves to exist.